Welcome back, everyone. Ready for another deep dive? Today, we're going to be tackling a fascinating topic, Poincaré polynomials.
Specifically, how they relate to plane curves.
Right. And we love to go deep here, so we're really going to dig into this.
Absolutely.
Our listener sent over a paper by Piotr Pokora. Have you had a chance to take a look?
Yeah, definitely. It's really intriguing stuff. Pokora makes some really interesting connections between Poincaré polynomials, which are typically used in topology, and some specific geometric properties of curves.
Okay, so for our listeners who might not be as familiar with Poincaré polynomials, could you give us a quick overview of what they are and why they're so important in math?
Sure. Think of it this way. You have a shape, any shape, right? It could be a curve, a surface, anything. The Poincaré polynomial is like a mathematical tool that helps us quantify the topological features of that shape.
Okay, so instead of just saying, hey, this curve is kind of twisty-turny, we have a precise way to measure that twisty-turniness.
Exactly. It's like a mathematical fingerprint that captures the essence of how the shape is connected, how many holes it has, that kind of thing.
That makes sense. So how does Pokora connect this concept to plane curves?
Well, he actually focuses on a specific type of plane curve called a free curve.
Free curves. What makes a curve free? Is it like floating around in space unrestrained?
Not exactly. It's more about the structure of the equation that defines the curve. A free curve has a very specific pattern in its defining equation.
Ah, so it's free in a mathematical sense, not a physical one.
Right. And what Pokora does is show how this freeness is deeply connected to the Poincaré polynomial of the curve.
Okay, I'm starting to see how these pieces fit together, but how does he actually use these polynomials to understand curves?
Well, he introduces this really ingenious technique that he calls the addition technique. Imagine you have two simple curves, and you know they're Poincaré polynomials. Pokora's technique gives you a formula to calculate the Poincaré polynomial of the curve you get by combining those two curves.
So it's like having two puzzle pieces and using a formula to figure out the shape of the bigger piece you get when you put them together.
Precisely. And the amazing thing is that this works even when the combined curve becomes super complicated. It's a powerful tool for breaking down complex curves into simpler parts that we can understand.
Okay, so that sounds really cool and practical, but I gotta admit, I'm a little lost on the technical details. Pokora defines the Poincaré polynomial of a plane curve using this formula, 1 plus d1t plus d1222. Can you break that down for us? What are all those symbols and what do they mean?
Sure. So d represents the degree of the curve, which essentially tells you how complex the curve is. The t is just a variable, and the exponents on t correspond to different dimensions of topological information.
Okay, so d is about the curve itself, and t is like a placeholder for different levels of detail about its shape.
Yeah, you got it. Now that's where things get interesting. It's called the Tjurina number, and it basically measures how singular or non-smooth the curve is.
So a curve with lots of sharp corners or cusps would have a higher Tjurina number.
Exactly. And the Tjurina number plays a crucial role in connecting the Poincaré polynomial to the concept of freeness. Pokora shows that these three things, the polynomial, the Tjurina number, and whether the curve is free or not, are all related in a very deep way.
So it's like the Tjurina number is the key that unlocks the secrets of these free curves.
That's a great way to put it. Now, to actually figure out if a curve is free, we use a theorem called the Duplessis-Wall theorem. It gives us a way to check for freeness by looking at the relationship between the curve's degree, the minimal degree of its Jacobian relations, and you guessed it, the Tjurina number.
Ah, so it all comes back to the Tjurina number. It's like this central hub connecting all these different ideas about curves.
Precisely. And once we know a curve is free, we can also determine its exponents. These are a pair of numbers that tell us even more about the curve's structure.
So the Poincaré polynomial helps us figure out if a curve is free, and then this freeness gives us even more insights into the curve's shape and properties.
You got it. It's a powerful combination.
Okay, so we've talked about these free curves, the Tjurina number, and how they relate to the Poincaré polynomial. But let's get back to that addition technique. How does Pokora actually formulate this idea of adding curves in terms of their Poincaré polynomials?
He actually gives us two main results. One is for calculating the Poincaré polynomial, and the other is for calculating the Betti polynomial when we add two curves. The Betti polynomial is another topological tool that gives us even more detailed information about the curve's structure.
So it's like having two different lenses, one giving us a broad overview and the other zooming in for a closer look.
That's a great analogy. And the formulas he derives are surprisingly simple. The Poincaré polynomial of the combined curve is essentially the sum of the Poincaré polynomials of the individual curves, plus an extra term that involves the number of points where the two curves intersect.
That's remarkably elegant. It almost seems too easy. Is there a catch?
Well, there is a crucial assumption. The curves need to have what we call quasi-homogeneous singularities.
Okay, quasi-homogeneous singularities. Those sound a bit intimidating. What are those exactly?
There is a special type of singularity that has a certain symmetry. You can think of them as well-behaved singularities.
Ah, so these specific singularities make the math work out nicely.
Exactly. They simplify the relationship between the Milnor number, which measures the complexity of a singularity, and the Tjurina number. For these types of singularities, the two numbers are actually equal.
Okay, so that equality is what makes the calculation smoother.
Exactly. It streamlines the whole process.
Got it. So we've got our Poincaré polynomials, these free curves, and Pokora's addition technique, which works beautifully when we have these quasi-homogeneous singularities. But I'm curious to see this addition technique in action. Pokora includes a few examples in his paper, right?
He does. Why don't we take a look at example 3.3?
Perfect. Let's dive in.
Okay, so in this example, he starts with an arrangement of 6 lines. He calls this C1. The way these lines intersect is crucial because it ensures we have those quasi-homogeneous singularities that we need.
All right, so we've got our first curve, C1, this arrangement of 6 lines. What's the second curve?
The second curve, C2, is a smooth conic.
Okay, a smooth conic. So how do we actually start using the addition technique?
Well, first, we need the Poincaré polynomials for each of the curves individually. Pokora gives us the Poincaré polynomial for C1 directly. It's 1 plus 5p plus 62.
Got it. So we've got the Poincaré polynomial for C1. What about for C2, the smooth conic?
Since C2 is smooth, its Poincaré polynomial is 1 plus t plus t2. That comes from the general formula for the Poincaré polynomial of a smooth curve.
Okay, so we have both of the individual Poincaré polynomials.
Yeah.
Now we're ready to use that addition formula, right?
Right. Remember, the formula says that the Poincaré polynomial of the combined curve is equal to the sum of the Poincaré polynomials of the individual curves, plus that extra term involving t and the number of intersection points, which Pokora calls r.
And what's R in this example?
In this case, r is 4, meaning the two curves intersect at 4 points.
Okay, so we have all the pieces we need. What does the calculation look like?
It looks like this. PC1 could C2 t, 1 plus 5t plus 6t2, plus 1 plus 2 plus t2 plus t1 plus 4 1t2.
Okay, so we're adding the two individual Poincaré polynomials together, and then we have that extra bit at the end of the t and the r. And when we simplify all that,
We get PC1 TT2 t equals 1 plus 7t plus 10t2.
that wasn't so bad. The formula really makes it straightforward.
It does. And there's something interesting about this resulting polynomial. It can be factored as 1 plus 2t, 1 plus 5t.
Okay, so we factored it. Why is that significant?
Well, that factorization tells us that the combined curve, C1, C2, is also a free curve. Remember, one of the ways we identify free curves is by looking for that specific type of factorization in their Poincaré polynomial.
Wow. So we started with a known free curve, C1, added another curve, C2, and through this addition process, we ended up with another free curve.
Exactly. It highlights the power of this technique. We can use it to not only calculate Poincaré polynomials, but also to uncover these hidden structures and relationships between curves.
That's pretty amazing. It feels like we're really starting to see how deep this rabbit hole goes.
We are, and there's so much more to explore.
This has been a great start to our deep dive, and I'm really looking forward to continuing this conversation.
Me too.
We'll be back with part 2 soon. Stay tuned.
Welcome back to our deep dive into Poincaré polynomials and plane curves.
It's great to be back. In part 1, we really got into the nuts and bolts of Pokora's work. Those free curves, the Tjurina number, that really cool addition technique.
And don't forget those quasi-homogeneous singularities, the ones that make all the math work out so nicely.
Right, they were a key piece of the puzzle. But now I'm curious to see where we can go from here. How does this research fit into the bigger picture of algebraic geometry and topology? It feels like we've just scratched the surface.
Yeah, I think you're right. Pokora's work really opens up some exciting avenues for further research. One thing that immediately comes to mind is exploring how his findings might apply to curves with more complex singularities. Remember, he mainly focused on those well-behaved, quasi-homogeneous ones.
Right, the nice ones.
Exactly. But what happens when we encounter more exotic types of singularities? Things could get a lot more complicated.
That's a great question. It seems like those quasi-homogeneous singularities were crucial for deriving those elegant addition formulas. Would those formulas still hold up if we relaxed that assumption? Or would we need to come up with entirely new tools to handle those more unruly singularities?
That's a question that's definitely worth exploring. It's possible that Pokora's formulas could be adapted or generalized to accommodate more complex singularities. Maybe we could introduce new terms or tweak the existing structure to capture that added complexity.
It's like we need to find a way to expand the language of those formulas to handle those trickier cases.
Exactly. Or maybe we need to develop entirely new approaches, leverage different topological invariants or algebraic techniques.
It's exciting to think about all those possibilities. It's like we're standing on the edge of a vast, uncharted mathematical territory. What other directions do you see this research heading in?
Another really interesting path is to explore connections with other areas of math. For example, Pokora's work hints at some intriguing links between the theory of plane curves and the study of hyperplane arrangements. Remember those triples of arrangements we talked about? They seem to pop up in both contexts.
Yeah, those triples kept appearing, almost like a hidden bridge connecting these two seemingly separate worlds.
Exactly. Investigating that bridge could lead to some really cool insights. Maybe we could develop new techniques for studying hyperplane arrangements, borrowing ideas from the tools and methods used in the theory of plane curves. Or maybe we'll find that certain properties of plane curves can be better understood through the lens of hyperplane arrangements.
It's amazing how these different branches of math, which might seem totally unrelated at first glance, can be so deeply intertwined.
Yeah, it's like they're different facets of the same mathematical jewel, each one reflecting and illuminating the others.
Okay, so we've talked about extending Pokora's work to more complex singularities and exploring connections with hyperplane arrangements. Are there any other research directions that come to mind?
Absolutely. One that I'm particularly interested in is whether Pokora's addition technique could be applied to other types of geometric objects. So far, we've been focused on plane curves, which are two-dimensional. But what if we considered surfaces, which are three-dimensional? Or even higher dimensional objects?
Wow, that's thinking big. I imagine things would get pretty mind-boggling when we start dealing with those higher dimensions.
Yeah, the challenges would definitely multiply, but the potential rewards could be enormous. Imagine being able to develop addition formulas for calculating the Poincaré polynomials of surfaces or even higher dimensional varieties. That would be a major breakthrough. It would open up a whole new way of understanding the topology and geometry of these objects.
It's like we'd be upgrading our mathematical toolkit from a simple set of hand tools to a sophisticated collection of power tools.
That's a great way to put it. And that's what makes Pokora's work so exciting. It's not just about solving specific problems. It's about giving us new frameworks and perspectives that can be applied to a wide range of mathematical challenges. Who knows what amazing discoveries might come out of it?
It's like Pokora has handed us a treasure map, and we're setting off on this grand mathematical adventure.
And who knows what mathematical treasures we'll find along the way. That's the beauty of research. It's a journey full of unexpected discoveries and those exhilarating aha moments.
Okay, so we've explored some exciting possibilities for future research based on Pokora's work. But let's shift gears a bit and address something I know our listeners are wondering. How does all this relate to real-world problems? It might seem like we've been deep in the realm of pure mathematics, but I'm sure there are practical applications hiding in there somewhere.
You're absolutely right. Even though Pokora's work might seem abstract at first glance, it has the potential to impact a lot of different fields, where understanding the geometry and topology of objects is really important. Think about things like computer graphics and computer-aided design, for example.
Okay, so like the stuff that makes video games and animated movies look so realistic.
Exactly. In those fields, being able to accurately represent and manipulate curves and surfaces is crucial. And Pokora's work gives us new tools for analyzing and understanding the properties of those curves, which could lead to more efficient algorithms and more accurate representations.
So his work could help create even more amazing visuals in movies and video games.
Potentially, yes. And it's not just about entertainment. Think about robotics, for instance.
Robots, how does that tie in?
Well, imagine you're designing a robot that needs to navigate a complex environment, like a warehouse or a factory floor. To plan efficient and safe paths for that robot, you need to have a deep understanding of the environment's topology. You need to know where the obstacles are, what shapes they have, how they're connected.
So Pokora's work could help robots get around better.
Exactly. And it goes even further than that. Think about tasks that require very precise movements, like surgery or manufacturing tiny electronic components. In those situations, understanding the shape and structure of the objects involved is absolutely crucial.
So a better understanding of curves could lead to more skilled and adaptable robots.
Precisely. And that's just a couple of examples. The potential applications of this research extend to fields like data analysis, materials science, even medical imaging. Anywhere where understanding the shape and structure of things is important.
Wow. It's amazing to think that these abstract mathematical concepts can have such a real and tangible impact on the world around us.
It really speaks to the power of mathematics as a language for understanding our universe.
Well said. So we've covered a lot of ground in part 2 of our deep dive. We've talked about potential applications of Pokora's work, discussed possible connections to other areas of math, and even explored some exciting avenues for future research.
And we're not done yet. We have some great questions from our listeners lined up for part 3, and I'm really looking forward to tackling those with you.
Me too. They're going to make us think even harder about this fascinating topic. So join us for part 3, where we'll dive into those listener questions, revisit some of the key concepts we've discussed, and wrap up our exploration with some final thoughts and reflections.
See you there.
Welcome back to our final deep dive into the fascinating world of Poincaré polynomials and plane curves. We've covered a lot of ground already, from those free curves and their special properties to that clever addition technique that Pokora introduced.
And we even ventured beyond the purely theoretical, exploring how this research might connect to other areas of mathematics and even have real-world applications. But we're not done yet. We have some excellent questions from our listeners, and I'm really eager to get your insights on these.
All right, let's dive into those listener questions then. Our first question comes from Alex. Alex asks, you've emphasized that Pokora's work centers on curves with quasi-homogeneous singularities. What makes these singularities so unique, and why are they so vital for his addition technique?
That's a great question, Alex. It gets right to the heart of what makes Pokora's approach so elegant. Remember, we talked about those two numbers, the Milnor number and the Tjurina number. Well, for quasi-homogeneous singularities, these two numbers are equal. And that equality makes the math much simpler. It allows us to express the Poincaré polynomial of a combined curve in a very concise way using Pokora's addition formula.
So it's like those quasi-homogeneous singularities provide a kind of mathematical shortcut that lets those formulas work their magic.
Exactly. They streamline the calculations and make everything much more manageable. Without that special relationship between the Milnor and Tjurina numbers, the math would get a lot messier.
Makes sense. Our next question comes from Sarah. Sarah asks, you talked about how Pokora's work could be applied to fields like computer graphics and robotics. Can you give us a more concrete example of how these mathematical concepts might actually be used in practice?
Of course, Sarah. Let's think about character animation for a moment. Imagine you're designing a character for an animated movie. You want to create a character that looks realistic, moves naturally, expresses emotions. To do that, you need to represent the character's shape very precisely. And that's where curves and surfaces come in.
So it's like sculpting with mathematical formulas, building up the character's form using these curves.
That's a great way to think about it. And the more accurately you can model those curves, the more lifelike and believable your character will appear on screen. Now, Pokora's work gives us new tools for analyzing and understanding those curves, which could lead to better algorithms for generating and manipulating them. For example, his addition technique could be used to combine simple curves into more complex shapes, giving animators more options and a finer control over their designs.
That's really cool. It smoother, more realistic animation thanks to advanced math.
Exactly. And in robotics, think about a robot arm that needs to pick up a delicate object, something with a complex shape. To do that successfully, the robot needs to understand the shape of the object, where to grasp it, how much force to apply. And that's where Pokora's work comes in. His research could help develop algorithms that allow robots to analyze and understand those complex shapes more effectively.
So it's like giving robots a deeper understanding of geometry so they can interact with the world more intelligently.
Precisely.
Okay, our final question comes from David. David asks, you've mentioned that Pokora's research opens up many intriguing questions. What are some of the most pressing questions that you believe future research should address?
That's a great question to end on, David, because it really highlights the fact that this is just the beginning. There's so much more to explore. One of the most pressing questions, I think, is how to extend Pokora's addition technique to those curves with more complex singularities. We talked about this earlier, but it bears repeating. Pokora focused mainly on curves with those well-behaved quasi-homogeneous singularities. But what about those singularities that are more wild and unpredictable? Can we adapt his formulas to those cases, or do we need entirely new tools?
Yeah, that's a big question mark. It's a real challenge, but also a very exciting one.
Absolutely. Another really interesting direction is to explore how Pokora's ideas might apply to other types of geometric objects. We've been focusing on plane curves, which are two-dimensional. But what about surfaces, which are three-dimensional? Or even higher dimensional objects? Can we come up with similar techniques and formulas for those?
It's like we're trying to generalize this whole framework to a much wider class of objects.
Exactly. And a third question that really fascinates me is this. What exactly does the Poincaré polynomial tell us about the geometry of a curve? I mean, we know it captures topological information, but can we develop a more intuitive visual understanding of what those numbers and variables actually represent?
It feels like we're trying to crack the code of this polynomial to really understand its deeper meaning.
That's a great way to put it. There are so many mysteries still hidden within those formulas waiting to be uncovered.
Well, folks, we've reached the end of our deep dive into the world of Poincaré polynomials and plane curves. I hope you've enjoyed the journey as much as we have.
It's been a real pleasure exploring these ideas with you. And who knows, maybe some of you listening will be the ones to answer those big questions we just talked about.
That's the beauty of math. There's always something new to discover. So keep those mathematical minds sharp, stay curious, and most importantly, never stop exploring the beauty and wonder of the mathematical universe. Until next time. All right. So today we're going to be diving into something pretty fascinating.
Yeah.
And we're going to be looking at plane curves and their Poincaré polynomials.
Yes.
And we're going to be using Piotr Pokora's paper on the addition technique for Betti and Poincaré polynomials of plane curves. You've sent over some excerpts, and I'm really interested to see what this addition technique is all about.
Yeah, it's a very clever method for calculating these polynomials, which, as you know, give us a way to understand the topology of these curves. It's like having a mathematical tool that lets you dissect the shape of a curve without actually needing to visualize it.
Okay, that sounds very intriguing.
Yeah.
Can we, before we get into that, can we just refresh our memories on what Poincaré polynomials are and why they're so important in this context?
Yeah, certainly. Think of a Poincaré polynomial as like a unique identifier for a curve, a kind of mathematical fingerprint that captures its essential topological features. It encodes information about the curve's degree, its singularities, and even the number of holes in the space surrounding it.
So it's like a compact way to summarize all the key characteristics of a curve shape, right?
Exactly. And what's fascinating is that these polynomials can reveal hidden relationships between seemingly different curves. For example, two curves that look completely different might have the same Poincaré polynomial, indicating some underlying topological similarity.
That's pretty cool. So Pokora's paper focuses on this technique for calculating these polynomials called the addition technique.
Yes.
What's the basic idea behind that?
The addition technique allows us to calculate the Poincaré polynomial of a complex curve by breaking it down into simpler curves and analyzing how they interact. It's like solving a jigsaw puzzle by first understanding the individual pieces and then seeing how they fit together.
I see. So instead of tackling the whole curve at once, we can divide and conquer.
Exactly.
Now, you mentioned that the paper includes some definitions, theorems, and examples. Shall we start with the definitions?
Absolutely. Let's lay the groundwork first.
Okay. So the first definition we have here is plane curve. I think we're all familiar with that.
Yes.
Can you just give us a formal definition?
Of course. A plane curve is essentially a set of points in a two-dimensional plane that can be described by an algebraic equation. Think of it as any shape you can draw on a flat piece of paper without lifting your pen lines, circles, ellipses, parabolas, and so on.
Right. So the classic conic sections we all learned about in school. Now, the next definition is Poincaré polynomial, PCT. This is where things start to get a bit more
complex.
Can you break down this equation for us?
Certainly. The Poincaré polynomial, denoted as PCT, is given by the equation PCT 1 plus d-1t plus d-2. Let's unpack this. That joiter represents the degree of the curve, which essentially tells us how many times the curve intersects a general line in the plane.
Okay.
A straight line has degree 1, a parabola degree 2, and so on.
So the degree gives us a sense of the curve's complexity.
Exactly.
The higher the degree,
Yes.
the more intricate the curve.
Yes, precisely.
What about T represents the total Tjurina number of the curve, which measures the complexity of the curve's singularities. Singularities are points on the curve where it doesn't behave smoothly, like cusps or points of self-intersection. The higher the Tjurina number, the more singular the curve.
So a smooth curve, like a circle, would have a Tjurina number of 0.
Exactly. And each term in the Poincaré polynomial equation captures a different aspect of the curve's topology. The 1 reflects the curve itself. The D1 term relates to its intersections with lines, and the D1 term incorporates information about its singularities. It's fascinating how this equation manages to pack so much information into such a compact form. Okay, let's move on to the next definition. The Betti polynomial, BMCT. How is this related to the Poincaré polynomial?
The Betti polynomial, denoted as BMCT, provides a different but related perspective on the curve's topology. It's given by the equation BMCT 1 plus E1t plus D plus E time, where E represents the Euler number. This number counts the holes in the curve's complement, the space left when you remove the curve from the plane.
So if a curve has more holes in its complement,
Right.
it'll have a higher Euler number,
Yes.
and that'll be reflected in its Betti polynomial.
Precisely. And just like the Poincaré polynomial, the Betti polynomial combines information about the curve's degree, singularities represented by the total Milnor number, and the Euler number to give us a deeper understanding of its topological structure.
It's like these polynomials are giving us X-ray vision into the curve's shape and structure.
Yeah.
Now, the next definition is quasi-homogeneous singularity. This sounds pretty technical. Can you break it down for us?
Imagine zooming in on a singularity on a curve.
Okay.
If it's a quasi-homogeneous singularity, it means we can zoom in or out, and the singularity will look basically the same. It's like a fractal. It has a self-similar structure. More formally, it means we can stretch or compress the coordinates around the singularity in a specific way, and the equation describing the curve knew that singularity will remain unchanged.
So it's like a kind of symmetry, but with scaling instead of rotations or reflections.
Right.
Why is this concept important for the addition technique?
This balance or symmetry is crucial because it allows us to break down the curve near the singularity into simpler pieces that we can analyze independently.
Okay.
This is key to the divide and conquer strategy of the addition technique.
Okay, that makes sense. Now, for quasi-homogeneous singularities, the Milnor and Tjurina numbers are equal.
Exactly.
Yeah.
This equality simplifies calculations and makes the relationship between the Poincaré and Betti polynomials even more elegant.
All right. The next definition is free curve. This seems to be a key concept in Pokora's paper. Can you explain what it means for a curve to be free?
A free curve has a special property related to its Jacobian syzygies, which are essentially relationships between the partial derivatives of the curve's defining equation.
Correct.
Without getting too technical, a free curve means that these relationships can be described in a very simple and elegant way. This simplicity makes free curves much easier to analyze.
So it's like free curves have a more organized algebraic structure,
Right.
which in turn makes their geometry more manageable.
Exactly. And this manageability is reflected in their Poincaré polynomials, which factor nicely into a product of linear terms. These linear terms are closely related to the exponents of the curve, which capture the essential complexity of its Jacobian syzygies.
So freeness simplifies the algebra,
Yes.
which gives us more insight into the geometry.
Exactly.
That's pretty neat.
Yeah.
Okay, I think we've covered all the definitions. Shall we move on to the theorems now?
Yes, let's delve into the heart of Pokora's work.
The first theorem we have here is theorem 1.2,
Right.
which seems to be the foundation for this addition technique.
Yes.
Can you give us a plain language explanation of what this theorem is all about?
Theorem 1.2 essentially says that if you have two curves that intersect at a finite number of points, and if the singularities of the combined curve are all quasi-homogeneous, then you can calculate the Poincaré polynomial of the combined curve by knowing the Poincaré polynomials of the individual curves and how they intersect.
So it's like a recipe for building up a complex curve from simpler ones.
Right.
And then figuring out its Poincaré polynomial.
Exactly.
Can you give us a bit more detail about how this works? What are the ingredients of this recipe?
The key ingredients are the Poincaré polynomials of the individual curves, the number of intersection points between them, and the fact that the singularities of the combined curve are all quasi-homogeneous. The theorem provides a specific formula that relates these ingredients to the Poincaré polynomial of the combined curve.
Okay, I'm starting to get the gist of it.
Mm-hmm.
But the proof of this theorem seems pretty involved.
It is, yes.
Can we walk through the key steps to see how it all comes together?
Absolutely. The proof starts by expressing the Poincaré polynomial of the combined curve, denoted as C1, C2, using the standard formula PCT, 1 plus D-1T plus D-1T2. Then we express the degree and the total Tjurina number of the combined curve in terms of the degrees and Tjurina numbers of the individual curves, taking into account their intersections.
So we're essentially breaking down the combined curve into its components and analyzing how those components contribute to its overall Poincaré polynomial.
That's a great way to put it. Now, the tricky part is handling the singularities that arise from the intersection of the two curves. This is where Lemma 3.1 comes into play. It gives us a formula for calculating the total Milnor number of the combined curve. And remember, for quasi-homogeneous singularities, the Milnor and Tjurina numbers are equal.
So we can use that lemma to connect the singularities of the individual curves to the singularities of the combined curve. What does Lemma 3.1 state?
Lemma 3.1 states that C1, C2 plus 2C1, C2, where R is the number of intersection points between the curves C1 and C2. We can substitute this into the Poincaré polynomial equation for the combined curve.
So we're essentially replacing the total Tjurina number of the combined curve with an expression involving the total Tjurina numbers of the individual curves and the number of intersections. What happens next?
From there, it's a matter of careful algebraic manipulation. We substitute the expressions for the degree and the total Tjurina number of the combined curve into the Poincaré polynomial formula, and after some simplification, we arrive at the formula stated in Theorem 1.2.
That's impressive. It's like a mathematical puzzle where all the pieces fit together perfectly to reveal the underlying structure. Now, Theorem 1.3 seems to be a parallel result, but for Betti polynomials. Could you elaborate on that?
You're absolutely right. Theorem 1.3 follows a similar structure to Theorem 1.2, but focuses on the Betti polynomial. It states that for two curves intersecting at a finite number of points, the Betti polynomial of the combined curve can be expressed in terms of the Betti polynomials of the individual curves, their degrees, Euler numbers, and the number of intersections.
So it's the same idea of breaking down the combined curve, analyzing its components, and then using a formula to calculate its Betti polynomial.
Exactly.
Does the proof follow a similar logic as well?
Yes. The proof of Theorem 1.3 closely mirrors that of Theorem 1.2. We start with the Betti polynomial of the combined curve, denoted as C1 ES C2, using its standard formula. Then we use Lemma 3.1 to express the total Milnor number of the combined curve in terms of the individual curves and the number of intersections. We also use the fact that for a plane curve, the Euler number can be expressed as E equals D by 1.
Okay, so we're using the same tools and techniques as in the proof of Theorem 1.2.
Exactly. And after some algebraic manipulation, we arrive at the desired form for the Betti polynomial of the combined curve, proving Theorem 1.3.
It's fascinating how these two theorems, with their parallel structures and proofs, highlight the interconnectedness of these seemingly different polynomials. They both provide a way to understand the topology of a complex curve by analyzing its simpler components.
It speaks to a deeper harmony in mathematics where seemingly different concepts often turn out to be intimately related.
All right, now I'm really curious to see how this addition technique works in practice. Shall we move on to example 3.3?
Let's do that. Example 3.3 provides a concrete illustration of how to apply these theorems.
Okay, so example 3.3 uses a conic and a line arrangement to demonstrate this addition technique.
Right.
Can you describe those two curves for us?
The conic, denoted as C2, is defined by the equation Q2 x, yz equals by2 plus y2 2z2 clue. This represents a smooth conic in the projective plane.
So a fairly straightforward curve. What about the line arrangement?
The line arrangement, denoted as C1, is a bit more intricate. It's defined by the equation $xyz equals x plus cyz plus cyxy plus x.
Okay.
This represents a set of 6 lines intersecting at various points in the projective plane.
Interesting.
Yeah.
So we have one smooth conic and a set of intersecting lines. How do we apply the addition technique to this combination?
First, we need to determine the Poincaré polynomials of the individual curves.
Okay.
The Poincaré polynomial of the conic C2 is straightforward. C2t, 1 plus k plus 2. This follows directly from the definition of the Poincaré polynomial and the fact that a smooth conic has degree 2 and no singularities.
So that's the fingerprints of our smooth conic.
Yes.
What about the line arrangement C1?
The line arrangement C1 requires a bit more analysis.
Okay.
By examining its intersections, we find that it has 3 points where 2 lines intersect, denoted as $2 3 to 3, and 4 points where 3 lines intersect, denoted as $3 equals 4, 4. Using this information and the fact that the degree of C1 is 6, we can calculate its Poincaré polynomial. PC1t equals 1 plus 5k plus 6t for thing.
Okay, so we've got the individual Poincaré polynomials for both the conic and the line arrangement.
Yes.
Now comes the addition technique, right?
Exactly.
Okay.
We also need to consider the number of intersections between the conic and the line arrangement, which is R st C1 C2 equals 4.
Okay.
Armed with these pieces, we can apply theorem 1.2.
Okay.
PC1 elo C2 T elo C1 T plus TC2 T plus T1 plus R1 T. Substituting the calculated values, we get PC1 re-T C2 play T2 1 plus 5T plus 6T plus U plus 1 plus T polyton 1 plus 7T plus 10 polytones.
So we've successfully calculated the Poincaré polynomial of the combined curve using the addition technique.
Yes.
But what does this polynomial tell us?
Interestingly, the resulting Poincaré polynomial 1 plus 7t plus 10 tau factors beautifully into 1 plus 2t, 1 plus 5t.
Okay.
This factorization strongly suggests that the combined curve C1 era C2 is a free curve.
That's interesting.
Yeah.
How can we be sure?
Pokora points out that this can be confirmed using a result from Duplessis and Wall.
Okay.
Which provides a criterion for the freeness of curves. Essentially, this criterion relates the freeness of a curve to the form of its Poincaré polynomial.
Okay.
In this case, the factorization of the Poincaré polynomial we obtained matches the form predicted by Duplessis and Wall's criterion, confirming that the combined curve is indeed a free curve.
That's pretty remarkable.
Yes.
By using the addition technique.
Right.
We not only calculated the Poincaré polynomial,
Exactly.
it also gained insight into the freeness of the combined curve.
Yeah.
Why is knowing that a curve is free so valuable?
Free curves have special properties that make them easier to work with algebraically.
Okay.
Their Poincaré polynomials factor in a predictable way, which reveals their exponents. And these exponents, in turn, tell us about the structure of their Jacobian syzygies.
So freeness simplifies the algebraic structure,
Exactly.
giving us more insight into the curve's geometry, right?
Precisely. And Pokora suggests in remark 3.4 that this addition technique can be a powerful tool for constructing new free curves.
Okay.
We can start with a known free curve, like the line arrangement in the example, and then add another curve to it. By analyzing the Poincaré polynomial of the resulting curve, we can check if it factors nicely, hinting at its freeness. It's like having a blueprint for creating these special curves with desirable properties.
That's a fascinating idea, using the addition technique to create new free curves now.
Yeah.
Moving beyond Poincaré polynomials.
Yeah.
Pokora also explores the behavior of Betti polynomials under this addition technique, right?
That's right.
Okay.
Theorem 3.5 presents a strikingly similar result to Theorem 1.2.
Okay.
But for Betti polynomials, it states that if you have 2 curves intersecting at a finite number of points, and if the singularities of the combined curve are all quasi-homogeneous, then the Betti polynomial of the combined curve can be calculated in a very similar way to the Poincaré polynomial.
So we can break down the combined curve, analyze its components, and then use a formula to calculate its Betti polynomial, just like we did with the Poincaré polynomial.
Exactly.
Okay, what are the key ingredients for this formula?
The formula involves the Betti polynomials of the individual curves.
Okay.
Their degrees, their Euler numbers, and the number of points where they intersect.
Okay, that sounds familiar.
Yeah.
It seems like there's a recurring theme here.
Right.
We break down the combined curve,
Exactly.
analyze its components,
Yeah.
and then account for their interactions.
That's a keen observation.
Okay.
Yeah, the proof of theorem 3.5 mirrors that of theorem 1.2.
Okay.
We start with the Betti polynomial of the combined curve and use lemma 3.1, which relates the total Milnor numbers to express everything in terms of the individual curves and their intersections.
Okay.
We also use the relationship between the Euler number, the degree, and the total Milnor number for a plane curve. E equals D11.
Okay.
Through some algebraic manipulation, we arrive at the desired form, showing that the Betti polynomial behaves nicely under this addition technique.
It's amazing how these two seemingly different polynomials,
Right.
Poincaré and Betti,
Yeah.
exhibit such similar behavior under this addition operation.
Indeed, it suggests a deeper underlying structure governing these polynomials and their connection to the geometry of the curves.
Now, Pokora mentioned something intriguing in remark 3.6 about Euler numbers. Can you elaborate on that connection?
Absolutely.
Okay.
Recall that the Euler number, often denoted as E, essentially counts the number of holes in a topological space.
Oh,
In our context, it's the number of holes in the curve's complement.
right, like the hole in the middle of a donut.
Precisely. Now, remark 3.6 highlights a beautiful consequence of theorem 3.5.
Okay.
If we evaluate the Betti polynomial identity at t equals -1,
Okay.
we get a relationship between the Euler numbers of the combined curve, the individual curves, and the number of intersection points.
Okay.
Specifically, it tells us that EMC1 cup C2 plus EMC2 plus R3, where MC represents the complement of the curve C.
So the Euler number of the combined curve is not just a simple sum of the Euler numbers of the individual curves.
Right.
There's this additional factor involving the number of intersections.
Exactly.
Okay.
This relationship reveals that when we combine curves, the number of holes in the resulting complement is influenced by how those curves interact with each other at their intersection points. It's a subtle but profound insight into how the topology of the combined curve emerges from its constituent parts.
It's amazing how a simple evaluation of the Betti polynomial at T101 can unveil such a deep connection between these topological invariants.
Yeah, it's quite remarkable.
Now, you mentioned earlier that Duplessis and Wall provided a criterion for the freeness of curves.
Right.
Can you tell us a bit more about that?
Certainly, Duplessis and Wall's criterion essentially states that a curve is free if and only if its Poincaré polynomial factors into a specific form.
Okay.
This form involves the exponents of the curve, which are a set of numbers that capture the essential complexity of the curve's Jacobian syzygies. Remember, the Jacobian syzygies are relationships between the partial derivatives of the curve's defining equation.
Right.
For a free curve, these relationships can be described in a very simple way, and the exponents essentially tell us how many generators are needed to describe these relationships.
So by looking at the factorization of a curve's Poincaré polynomial, we can determine whether or not it's a free curve.
Exactly.
Okay.
And this criterion is a powerful tool for identifying free curves, especially when combined with techniques like the addition technique, which allow us to construct new curves from simpler ones.
This is all starting to make sense.
Good.
We can use the addition technique to build up complex curves from simpler ones.
Right.
Calculate their Poincaré and Betti polynomials,
Yes.
and then use Duplessis and Wall's criterion to check if they're free.
Exactly.
There's like a toolbox for exploring the world of plane curves and their topological properties.
That's a great analogy.
Okay.
Yeah.
Let's shift gears a bit and talk about a specific type of curve called a line arrangement.
Okay.
Pokora devotes a section of his paper to these curves.
Right.
What are line arrangements and why are they important in this context?
A line arrangement is simply a collection of lines in the plane.
Okay.
It might sound simple, but line arrangements exhibit surprisingly rich and complex behavior. And they've been a subject of intense study in mathematics for centuries.
That makes them so interesting.
Line arrangements provide a fertile ground for exploring fundamental questions about geometry, topology, and combinatorics. For example, how many points of intersection can a given number of lines create?
Okay.
How does the arrangement of the lines affect the topology of the resulting space?
So line arrangements offer a way to study complex mathematical phenomena in a relatively simple setting.
Precisely.
Yeah.
And in the context of Pokora's work, line arrangements are important because they often serve as building blocks for constructing more complex curves.
Right. So understanding line arrangements is essential for applying the addition technique effectively.
Exactly.
Okay.
Pokora dedicates section 4 of his paper to line arrangements,
Okay.
focusing on a specific type called supersolvable line arrangements.
What makes a line arrangement super solvable?
Supersolvability is a property related to the way the lines in the arrangement intersect. Without delving into the technical details, a supersolvable line arrangement has a hierarchical structure that makes its combinatorial and topological properties easier to analyze.
So it's like a well-organized line arrangement that's easier to work with.
That's a good way to think about it.
Okay.
And in theorem 4.3, Pokora shows that the Poincaré polynomial of a supersolvable line arrangement can be expressed in a very specific form that reflects its hierarchical structure.
Interesting. So we have a special formula for calculating the Poincaré polynomial of these supersolvable line arrangements.
Exactly.
Oh, yeah.
And this formula is a valuable tool for studying the properties of these arrangements.
Okay.
For example, it can help us understand the relationship between the arrangement's combinatorics, the way the lines intersect, and its topology, the shape of the resulting space.
This is all fascinating stuff. I'm really starting to appreciate the depth and complexity of this area of mathematics. Now, I'm curious about those exponents you mentioned earlier.
Yeah.
Can you elaborate on what they are and why they're important?
Certainly. The exponents of a curve, as I mentioned earlier, are a set of numbers that capture the essential complexity of the curve's Jacobian syzygies. Remember, the Jacobian syzygies are relationships between the partial derivatives of the curve's defining equation.
Right.
For a free curve, these relationships can be described in a very simple way, and the exponents essentially tell us how many generators are needed to describe these relationships.
So the exponents give us a measure of the complexity of the algebraic structure of the curve, which in turn influences its geometry.
Precisely.
Okay.
And one of the remarkable results in Pokora's paper is that the addition technique preserves the exponents of the curves involved.
What do you mean by preserves the exponents?
It means that if we combine two curves using the addition technique, the exponents of the resulting curve can be determined directly from the exponents of the individual curves. Yeah. This is stated in theorem 5.1.
That's pretty powerful.
Yes.
So we don't have to go through the whole process of calculating the Jacobian syzygies and their generators for the combined curve.
Right.
We can just use the exponents of the original curves.
Precisely.
Yeah.
And this preservation of exponents has some interesting consequences.
Okay.
For example, it implies that if we combine two free curves using the addition technique, the resulting curve will also be free.
That makes sense.
Yes.
If the exponents, which capture the freeness of the curve, are preserved, then the combined curve should also inherit that freeness.
Exactly. And this result highlights the elegance and power of the addition technique. It allows us to build up complex curves from simpler ones while preserving their key properties.
It's like a mathematical Lego system where we can combine pieces to create something new and intricate while still understanding how the individual pieces contribute to the whole.
That's a great analogy.
Okay.
And this Lego system approach opens up exciting avenues for research. We can use the addition technique to explore the vast landscape of plane curves, constructing new curves with specific properties, and unraveling the intricate connections between their algebra, geometry, and topology.
It's amazing how Pokora has managed to create this elegant framework for understanding the structure of plane curves. I'm curious, are there any practical applications for these ideas?
Absolutely. While these concepts might seem abstract at first glance, they have applications in fields like computer graphics, robotics, and even coding theory.
Can you give us some specific examples?
Certainly. In computer graphics, for instance, understanding the topology of curves and surfaces is essential for creating realistic 3D models and animations.
Okay.
The Poincaré polynomial and the Betti polynomial can provide valuable information about the shape and structure of these objects, helping to optimize rendering algorithms.
That makes sense.
Yeah.
What about robotics?
In robotics, the ability to plan the motion of a robot arm or a mobile robot through a complex environment often involves understanding the topology of the obstacles and the free space.
Okay.
Tools from algebraic geometry, like those discussed in Pokora's paper, can be used to represent and analyze these spaces efficiently, leading to more robust and intelligent robot motion planning algorithms.
So these seemingly abstract mathematical concepts can have very real and tangible applications
Yeah,
in engineering and technology.
precisely.
Okay.
And in coding theory, the study of error-correcting codes, which are used to protect data from noise and corruption,
Okay.
often involves working with algebraic curves defined over finite fields. The properties of these curves, including their Poincaré polynomials,
Right.
can be used to design and analyze efficient coding schemes.
That's fascinating.
Yeah.
I never would have guessed that these ideas could be applied in such diverse fields.
It's quite remarkable.
Now, before we wrap up,
Sure.
I'd like to ask you a bit about the broader context
Okay.
of Pokora's work. How does this paper fit into the larger landscape of research in algebraic geometry?
Pokora's work builds on a rich tradition of research in algebraic geometry, dating back to the 19th century.
Okay.
The study of plane curves in particular has been a central theme in this field, with deep connections to other areas of mathematics, such as topology, combinatorics, and number theory.
Can you give us some historical highlights or landmark results that led up to Pokora's work?
Certainly.
Okay.
One of the early milestones in the study of plane curves was the development of the concept of genus by Bernhard Riemann in the mid-19th century.
Okay.
The genus is a topological invariant that measures the number of holes in a surface, and it turns out to be closely related to the degree and the number of singularities of a plane curve.
So the idea that the topology of a curve is related to its algebraic properties goes back a long way.
It goes back a long way.
Okay.
Another major breakthrough came in the early 20th century with the work of Oskar Zariski, who developed the foundations of modern algebraic geometry. Zariski introduced the concept of a singularity and laid the groundwork for understanding how singularities affect the geometry and topology of algebraic varieties, including plane curves.
And how does Pokora's work build on these earlier ideas?
Pokora's work can be seen as a modern extension of these classical ideas.
Okay.
The Poincaré polynomial and the Betti polynomial, which are central to his paper, are modern tools that allow us to capture more refined information about the topology of curves than the genus alone.
Okay.
And the addition technique, which is the main focus of his paper,
Right.
provides a powerful method for calculating these polynomials and exploring their properties.
So it's a beautiful example of how mathematical research builds on itself.
Right.
With new ideas and techniques emerging from earlier foundations.
Precisely. And this ongoing process of discovery is what makes mathematics such a vibrant and exciting field.
Well, I think we've covered a lot of ground today.
Yeah.
From the basic definitions of plane curves and their polynomials to the intricacies of the addition technique and its applications.
Yes.
I feel like I've gained a much deeper appreciation for the beauty and power of algebraic geometry.
It's been a pleasure sharing these ideas with you.
Well, thank you.
I hope our listener has enjoyed this deep dive into the world of plane curves as well.
I'm sure they have.
Yeah.
So to wrap things up,
Sure.
what's the key takeaway message you want our listener to walk away with?
The key takeaway is that mathematics is a powerful tool for understanding the world around us, even in seemingly abstract realms like algebraic geometry.
Okay.
The concepts we've explored today, while they might seem technical at first glance, have deep connections to real-world applications in fields like computer graphics, robotics, and coding theory.
And they highlight the beauty and interconnectedness of different areas of mathematics,
Right.
from algebra and geometry to topology and combinatorics.
Exactly.
Yeah.
So keep that sense of wonder alive, and who knows, maybe you'll be the one to make the next breakthrough in this fascinating field.
Well said.
Yeah.
And as always, thanks for joining us on this mathematical adventure.
My pleasure.
We'll see you in our next deep dive. All right, so get ready. We're about to take a deep dive into these things called Poincaré polynomials, and we're going to look at how they, how they change when we start combining curves using this technique they call the addition technique, right? And it's pretty amazing. You know, you can really start to get a feel for how these super complicated geometric shapes you can really break them down into these simpler pieces.
Yeah, yeah, absolutely. It's like this idea of, building up complexity, right? From like simpler building blocks, right? It's a common theme you see all over in mathematics. But what's really, really neat here is how this addition technique that we're going to be looking at for these curves, it actually mirrors this similar technique that's used when you're studying these things called hyperplane arrangements. So there are these parallels, right, that kind of suggest there might be this this deeper connection hiding underneath, and that's something we're going to kind of try to unravel as we go through this.
I'm always up for a good mathematical mystery. So we're basically on this hunt for patterns and formulas, right, that kind of pop up when we start combining these curves, especially when we're dealing with these special ones, the curves with these quasi-homogeneous singularities, right? It's kind of like putting a puzzle together, where each piece we find gives us a little bit more of the big picture.
Exactly. You got it. But before we get too far ahead of ourselves here, we should probably make sure we're all on the same page, make sure we all know what we're talking about in terms of some key definitions here.
Definitely. Lay it on us. Where should we start?
All right. Okay. So first up, we got to talk about these things called isolated singularities. And these happen, they happen on curves, right? And you can picture these as like points on the curve where things get a little wild, where the curve kind of takes this sharp turn or something and creates, maybe a cusp or a crossing or just some other kind of behavior that isn't smooth. They're kind of like the troublemakers in this otherwise smooth world of curves. You know what I mean?
Gotcha. So it's kind of like having a jagged edge on an otherwise perfectly smooth surface.
Precisely. Yeah, that's a great way to put it. Now, to measure how wild these jagged edges are, right, we use these things called the Milnor and Tjurina numbers. And these numbers, they basically give us information about how the curve is behaving around these singular points. So you don't kind of think of them as a way to quantify how sharp those turns are that we were talking about.
Okay. So it's like we're putting a number on just how much the curve is deviating from being perfectly smooth at these specific points.
Exactly, precisely. Now, each singular point, right, each one has its own local Milnor and Tjurina numbers. And then by adding all of those up over all the singular points on the entire curve, well, that gives us what we call the total Milnor and total Tjurina numbers for the whole curve.
Okay, that makes sense. So how do these Milnor and Tjurina numbers, how do they relate to that special type of singularity that we mentioned, the quasi-homogeneous singularity?
Right. Well, for these special types of singularities, the really neat thing is that the Milnor and Tjurina numbers are actually the same at each singular point.
Yeah.
So it simplifies things quite a bit. And this simplification even carries over to the total numbers too, meaning that the total Milnor number is just straight up equal to the total Tjurina number for curves with these well-behaved singularities,
Oh, cool.
Yeah.
So that definitely simplifies things, right? When we're working with these quasi-homogeneous singularities. Okay, but now where does the Jacobian syzygies come in? I got to admit, those sound kind of intimidating, huh?
Yeah, I know, right? The name itself sounds a little technical, I'll give you that. But they actually play a super important role in understanding the algebraic structure of our curves, and specifically when we're dealing with a special type of curve called a free curve. And these free curves, they have some really, really nice properties that make them desirable to work with. Let's just say that. So think of Jacobian syzygies as a way to describe relationships between the partial derivatives of that polynomial that defines our curve, right? And these relationships, they can actually tell us a lot about the geometry of that curve.
Okay. I think I'm starting to see the connection here.
Yeah.
So how do we actually know if a curve is free? It sounds like being free is a good thing for a curve.
Yeah, you're right. Free curves, they're pretty special. So one way to define them is using this concept of saturated Jacobian ideals. But there's a more accessible way to understand it, and it's thanks to this theorem called the Duplessis-Wall theorem. And this theorem, it connects the idea of freeness to the total Tjurina number of the curve, the degree of the curve, and this thing called the minimal degree of non-trivial Jacobian relations, or MDR for short. So it's basically like, it gives us this handy checklist, right, to determine if a curve is free.
Oh, cool. So it's like a litmus test for freeness.
Yeah.
What's also interesting is that this theorem, this Duplessis-Wall theorem, right, it links freeness to the curve's exponents. What exactly are these exponents?
Right, right. So the exponents, they're basically like this pair of numbers, that further characterize the structure of a free curve.
Hmm.
And they really come into play when we start looking at this thing called the Poincaré polynomial, which is, well, it's kind of the star of our show today.
Right. The Poincaré polynomial. Can you remind me again what this polynomial is all about?
Sure. So the Poincaré polynomial, it's given by this formula, right? It's PCT 1 plus D-1T plus D1T2.
Hmm.
And in that formula, D is the degree of the curve and C is the total Tjurina number. And this polynomial, well, it's this powerful tool, it basically encapsulates information about the topology of our curve.
Got it. So the Poincaré polynomial takes into account the curve's degree and its total Tjurina number, which, like we said, it simplifies a lot for those special quasi-homogeneous singularities, right?
Exactly, you got it. And remember how we were talking about free curves? Well, the Duplessis-Wall theorem, it actually tells us that the Poincaré polynomial of a free curve, it factors really nicely, right, into this product of two simpler polynomials. And those are determined by those exponents that we just talked about.
Uh-huh. Now it's all coming together. But how does this addition technique actually fit into all of this? Like, how do we actually combine curves?
Yeah, that's where things get really interesting. So we're going to explore what happens to the Poincaré polynomial when we combine two curves that intersect, at a certain number of points. And our first big theorem, theorem 1.2, it actually reveals this surprisingly simple formula for how this works.
Okay, now you've really got me on the edge of my seat. What does this formula actually look like?
All right, so it states that for two curves, right, we'll call them C1 and C2. And these curves, they have those nice quasi-homogeneous singularities we talked about, and they intersect at, let's say, R points. Okay, so the formula says that the Poincaré polynomial of their union, that's C1, C2, it's given by PC1 ESC2 PC1 T plus PC22 plus T1 plus R1 T2. So basically, the Poincaré polynomial of this combined curve, it's directly related to the individual polynomials plus this extra term that depends on how many points they intersect at.
Wow. So we can basically just build up the Poincaré polynomial of this more complicated curve, right? Just on the polynomials of its simpler parts. That's pretty elegant. But how do we even begin to prove a formula like that?
Yeah, it's a good question. So the proof, it relies on this clever interplay between the definition of the Poincaré polynomial and this key result called lemma 3.1. And this lemma, it connects the total Milnor numbers of the curves before and after we combine them. And it really shows how interconnected all these different mathematical concepts are.
So lemma 3.1, it's like a bridge.
Yeah.
Between the individual curves and their union. It seems like there's a lot to unpack there. Can you tell me more about what it says?
Of course. So lemma 3.1, it states that for two curves, C1 and C2, right, that intersects at OR points, well, the total Milnor number of their union, that's C1 and C2, it's equal to, the sum of their individual total Milnor numbers plus 2 times the product of their degrees minus the number of intersections. So it's basically quantifying how the wildness of the combined curve, right, is related to the wildness of its components and how they interact.
Okay, so it's like we're accounting for all the extra singularity that comes from when the curves intersect.
Precisely, yeah. And this accounting, it's actually super important for proving theorem 1.2. We start with the Poincaré polynomial of the union, right? And we expand it using its definition. Then we strategically apply lemma 3.1 to replace the total Milnor number of the union. And then through some clever algebraic manipulation, well, we arrive at the formula we want. And it really reveals the additive nature of the Poincaré polynomial under this addition technique.
It sounds like a whole symphony of algebraic maneuvers, haha.
Yeah.
But I'm guessing there's more to it than just, rearranging terms. There must be some subtle tricks involved, right?
Oh, yeah, you're definitely right. The proof, it involves this delicate dance, You have to group terms strategically, and you have to use the fact that the total Tjurina number equals the total Milnor number for our special quasi-homogeneous singularities. It's all about finding the right connections between all the pieces of the puzzle.
It kind of reminds me of those elegant mathematical proofs, where it all seems so obvious in hindsight, but it takes a spark of genius to discover it in the first place.
Exactly, and that's what makes math so captivating, right? It's about finding those hidden connections and those unexpected relationships that illuminate these deeper truths.
I'm already feeling like we've uncovered some hidden gems. So we've explored this theorem 1.2 and how lemma 3.1 how it plays this crucial role in the proof. But before we move on, I'm really curious about this example 3.3, the one where we added a smooth conic to a specific line arrangement. Can you walk me through how we actually calculate the Poincaré polynomial in that case? It seems like a great way to see this addition technique in action.
Absolutely. Let's dive into the specifics. So remember, we have this this line arrangement. We called it C1, right? And it consisted of 6 lines. And then we had the smooth conic, which we called C2. Now we know that C1, it's a free curve, and its Poincaré polynomial is given by PC1t equals 1 plus 5p plus 6t2.
And if I remember correctly, the Poincaré polynomial for the smooth conic C2, it's PC22 equals 1 plus t2, right?
You got it. Perfect. Now, these two curves, they intersect at 4 points. And using theorem 1.2, we can directly calculate the Poincaré polynomial of their union. That's C1 near C2.
So we just add the individual Poincaré polynomials, PC1t and PC2t.
Yeah.
And then we add T1, and finally we add 3 times T2 because we have 4 intersections, right?
Precisely. Exactly. So that gives us PC1C2t, 1 plus 5t plus 6t2 plus 1 plus t plus t2 plus t1 plus 3t2. And if we simplify that, it comes out to PC1C2t, 1 plus 7t plus 10t2.
Okay, yeah, that seems pretty straightforward. But is there anything special about that resulting polynomial?
There is. So this polynomial, it actually factors really nicely. It factors as 1 plus 2t, 1 plus 5t. And that actually suggests that C1, C2, it might also be a free curve. This factorization, it's a strong hint, you know, and it's actually confirmed by another result known as theorem 1.3, which we'll get to a little bit later.
So we started with a free line arrangement, added a smooth conic, and we ended up with another free curve. That's pretty amazing how this addition technique it kind of preserves this freeness property, right?
It is. It is. It's a beautiful illustration of how these seemingly simple operations, right? They can lead to these really profound insights, and they can connect these concepts that might seem totally separate at first glance.
This journey through these Poincaré polynomials is already proving to be pretty insightful. But now I'm wondering if we can use this addition technique for these Poincaré polynomials. Can we do something similar for other polynomials that describe the topology of these curves? I'm particularly curious about this Betti polynomial.
That's an excellent question, and it leads us to even deeper waters, you know. And you might have guessed it, but we can actually develop a similar addition formula for the Betti polynomial, and that provides this different but equally fascinating perspective on the topology of our curves and their complements.
Now you've really got me curious. What secrets does this Betti polynomial hold, and how does it connect to this addition technique? Well, that's a story for the next chapter of our deep dive, but I can tell you it's a story full of intrigue and elegance and some really surprising connections. Okay, so we've kind of laid the groundwork with these Poincaré polynomials and that intriguing behavior they have with this whole addition technique. Now let's jump into the world of these Betti polynomials. So what exactly are these Betti polynomials, and why should we even care about them?
Right. So Betti polynomials, they basically offer us another way to look into the topology of our curves. But instead of focusing on the curve itself, they actually describe the topology of the complement of the curve in the plane. And we denote that as MC, right? So you can kind of think of it as studying the holes, you know, or the voids that are left behind by the curve in that surrounding space.
Oh, okay. So it's like taking a negative image of the curve, like focusing on what's not there. That's a pretty cool shift in perspective. But what kind of information does the Betti polynomial actually give us about this complement?
Yeah, so it basically captures the number of holes of different dimensions in the complement. And in the case of plane curves, we're essentially dealing with 2 types of holes. We have the 0-dimensional ones, which correspond to connected components, and then we have the 1-dimensional ones, which correspond to loops that can't be contracted to a point.
So counting the number of islands, right, and then the number of circular paths that can't be, shrunk down to a single point in that space surrounding the curve. That's a pretty intuitive way to think about it.
Exactly. Yeah, that's a great way to put it. And the Betti polynomial, it basically presents all this information in this nice, neat package, right? With each term corresponding to the number of holes of a specific dimension. And the beauty of it, right, is that this polynomial, it captures so much information, a lot of topological information about the complement, all in this single expression.
Sounds like a powerful tool. So now I'm really curious about this addition formula for these Betti polynomials. Does it look anything like the one we saw for the Poincaré polynomials?
You might be surprised. So theorem 1.3, it reveals this strikingly similar addition formula for the Betti polynomial. So for two curves, right? C1 and C2 again intersecting at, let's say, R points. Well, the Betti polynomial of their union, that's C1, C2, it's given by this: BMC1C2, BMC1T plus BMC2 plus T1 plus R1T2.
Wow. Okay, yeah, that's almost identical to the formula for the Poincaré polynomials. It's pretty amazing how both of these polynomials, how they both exhibit this additive behavior, right, with this addition technique.
Yeah, it really is. And this striking similarity, it really hints at a deep connection between these two polynomials that seem so different on the surface, right? It suggests that the way a curve is, embedded in the plane and the structure of its complement, well, they're really closely related,
Yeah.
in ways that we're just starting to understand, I think.
It's like they're speaking the same language, right? Mathematically speaking.
Yeah.
Even though they're describing these different aspects of the curve.
Yeah, exactly. You hit the nail on the head. But the connection, it goes even deeper than that, actually. Remember remark 3.6, it pointed out that if we evaluate both the Betti and the Poincaré polynomials at t equals 1, well, we actually get this relationship between the Euler numbers of the complements of those curves.
Right. The Euler number, that classic topological invariant that counts the number of holes in a space, taking into account, all the different dimensions. So we have this bridge, right, between these polynomials and this fundamental topological property.
Precisely. Exactly. And it really makes you wonder, why does this specific evaluation at t equals 1, why does it link these polynomials to the Euler number? It suggests there's this deeper interplay going on, right, between the algebra of these polynomials and the topology of the curve and its complement.
It's like we're seeing the shadows of this more profound mathematical structure, right? Something that connects these seemingly separate concepts in this harmonious dance or something.
That's a beautiful way to put it, and that's what makes this area of research so exciting. We're uncovering these hidden connections, and we're starting to glimpse this more unified picture of geometry and topology.
Okay, so we've established that both the Betti and the Poincaré polynomials, they both have these elegant addition formulas. But how do we actually prove this theorem 1.3? Is it similar to the proof of theorem 1.2?
Yeah. The proofs, they actually share a similar strategy. We basically leverage the definition of the Betti polynomial, which involves the total Milnor number, the degrees of the curves, and the number of their irreducible components. And just like before, lemma 3.1 with its relationship between those total Milnor numbers, it plays a crucial role again.
It seems like lemma 3.1, it's a real workhorse in these proofs.
Yeah.
It's bridging the gap between those individual curves and their union. Right?
Yeah.
Providing this crucial link to establish these addition formulas.
You got it. Exactly. So the proof of theorem 1.3, it involves, carefully substituting terms from lemma 3.1 into that Betti polynomial expression. And then you got to do some clever manipulation and regrouping of terms. It's a bit like solving a puzzle, where you got to fit all the pieces together in just the right way to reveal the hidden pattern.
I can appreciate the intricate dance of logic and algebra going on there. It's like a detective story, right? Where each step brings us closer to solving the mystery.
I love that analogy. And speaking of solving mysteries, let's go back to that example 3.3 where we added that smooth conic to that free line arrangement. Remember, we already saw how the Poincaré polynomial of that resulting curve, how it factored so nicely, right? And that hinted at its freeness. But does the Betti polynomial tell the same story?
That's a great question. It would be cool to see if the Betti polynomial also suggests that the combined curve is free.
Yeah, let's dive into those calculations and see what we find. So first, we got to figure out the Betti polynomials of those individual curves. So for the line arrangement C1, its Betti polynomial is given by BMC1t equals 1 plus 5t.
And for the smooth conic C2, it's simply BMCT1, right? If
Yeah.
I'm not mistaken.
You're exactly right. Perfect. Now, using theorem 1.3, we can calculate the Betti polynomial of their union. That's C1, C2. It's given by BMC1 and C2t, BMC1t plus P1 plus R1t2, where R is that number of intersections, which is 4 in this case.
So if we plug in those values, we get BMC1 EC2t, 1 plus 5t plus 1 plus t1 plus 3t2, which simplifies to BMC1 EC2 equals 1 plus 6t plus 3t2.
Exactly. Now, the question is, does this polynomial suggest that the combined curve is free?
It doesn't seem to factor as nicely as that Poincaré polynomial did. Does that mean the combined curve isn't free after all?
Not necessarily. So while the Betti polynomial doesn't, directly reveal that freeness property as explicitly as the Poincaré polynomial does, there are other ways to confirm it. In fact, theorem 1.3 from another paper, it actually guarantees that the resulting curve is indeed free.
So even though the Betti polynomial doesn't factor as neatly, it still gives us valuable information about the topology of the complement, right? And we can use other results to kind of piece together the complete picture.
Precisely. Yeah. It's like having all these different tools in our mathematical toolbox, and each tool offers this unique perspective, right? And it helps us solve these different aspects of the puzzle.
I'm really loving this journey of discovery. But now I'm wondering if these addition formulas hold for curves in the plane. Can we extend these ideas to higher dimensions? Like, can we even talk about Poincaré and Betti polynomials for surfaces, or even higher dimensional objects?
That's a fantastic question, and it takes us into this whole realm of algebraic topology. Where these concepts, they generalize in these really beautiful and profound ways, but that's a story for another deep dive.
I can't wait to explore those higher dimensional realms. For now, let's take a step back and kind of revisit the key takeaways from our discussion of these Betti polynomials. They really offer this fascinating lens, to view the topology of these complements of curves and their behavior under this addition technique. Well, it reveals these deep connections to the Poincaré polynomials and the Euler number.
Absolutely, and this whole interplay between algebra, geometry, and topology, it's what makes this area of mathematics so captivating, right? It's like we're uncovering this hidden language that speaks to the fundamental structure of shapes and spaces.
It truly is a symphony of mathematical ideas. But I'm curious, what are some of the unanswered questions in this area? What mysteries are mathematicians still grappling with?
Well, one of the big challenges is to understand when and why these addition formulas hold in more general settings. We've been focused on these curves with quasi-homogeneous singularities, but what about curves with more complicated singularities? Can we find similar formulas?
And what about those higher dimensional spaces that we hinted at? Do these ideas extend beyond curves in the plane?
Yeah.
Are there analogous polynomials for surfaces or even higher dimensional objects?
Those are all fantastic questions, and they represent active areas of research. Mathematicians are developing new techniques and new theories to tackle these challenges and push the boundaries of our understanding.
It's exciting to think that we've only just scratched the surface of this vast and intricate mathematical landscape. There's so much more to explore, so many more connections to uncover.
Exactly. And that's the beauty of mathematics, right? The journey of discovery never ends. There's always a new challenge, a new perspective, a new layer of beauty waiting to be revealed.
So we've been on quite the journey here, right? Exploring these Poincaré and Betti polynomials. We uncovered these really elegant addition formulas, and those formulas show us how these polynomials actually change when we combine curves. It's kind of fascinating how we can understand the topology of these complex curves by just breaking them down into these simpler pieces.
Yeah, absolutely. And what's really remarkable is that these formulas, they hold for both of these polynomials, right? We have the Poincaré polynomial, which captures information about, about the curve itself, and then we have the Betti polynomial, which describes the topology of its complement, and it really highlights this deep connection between those two aspects of a curve, which might seem pretty different at first glance.
Yeah, it's like these polynomials are two sides of the same coin, each one revealing a different facet of that same geometric object. But the connection goes even further, right?
Yeah.
We also talked about the Euler number and its relationship to these polynomials.
Yeah, exactly. So evaluating both Poincaré and Betti polynomials at t on is 1 p, it actually gives us this relationship between the Euler numbers, the complements of those curves, and it's a really beautiful example of how these seemingly disparate mathematical concepts can be so intertwined in these really surprising ways.
It's like these polynomials. They hold this secret code, that unlocks this deeper understanding of the topology of those curves and their complements. But I'm curious, what's the significance of evaluating at t-1? Why does that specific value connect these polynomials to the Euler number?
That's a great question, and it's one that really delves into the heart of algebraic topology. Without getting too technical, it boils down to the fact that evaluating at t in actual 1, it essentially captures this alternating sum of the Betti numbers, and that's a fundamental way to actually define the Euler number.
So it's like we're extracting this key piece of topological information from these polynomials just by plugging in this special value. It's amazing how a single number can tell us so much about the structure of a space.
Yep.
Yeah, it really is. It's a testament to the power of mathematical abstraction, right? We can encode these complex geometric and topological properties into these elegant polynomials, and then we can extract meaningful insights just through these simple operations like evaluation.
This deep dive has really opened my eyes to the beauty and just the interconnectedness of mathematics. But I can't help but wonder, what are some of the practical applications of these ideas? Like how does this knowledge actually translate into real world problems?
Yeah, that's a question that comes up a lot, right? When you're exploring these seemingly abstract mathematical concepts. But the truth is, these ideas have far-reaching implications in lots of different fields, actually.
Can you give me some specific examples?
Sure. So one area where these concepts find applications is in computer graphics and computational geometry.
Mhm.
Understanding the topology of curves and surfaces, it's really crucial for creating these realistic and efficient representations of objects in computer systems.
Oh, so these polynomials can help us create those more lifelike animations and simulations that we see, right?
Exactly, yeah. They provide this mathematical framework for analyzing and manipulating shapes in those virtual environments. And another area where these ideas are relevant is in robotics and motion planning. When you're designing these robots that navigate complex environments, well, understanding the topology of the obstacles in the free space, it's essential.
It's like giving robots a mathematical compass to help them find their way.
Right. Precisely. Yeah, these topological tools, they give us this way to quantify and reason about the connectivity and the structure of that space, and that allows those robots to plan efficient and safe paths.
It's really fascinating to see how these abstract mathematical concepts have such tangible real world applications. It reminds us that math isn't just this theoretical pursuit. It's a powerful tool for understanding and shaping our world.
Exactly. Yeah, mathematics, it provides this universal language. It transcends these specific domains. It's a language that speaks to those underlying patterns and structures that govern our universe.
As we wrap up this deep dive, I'm left with this sense of awe and wonder. We've only just scratched the surface of this vast and intricate mathematical landscape, and yet we've uncovered so much beauty and interconnectedness, right?
Yeah, absolutely. And that's the beauty of mathematics, right? The journey of discovery never ends. There's always more to explore, more connections to uncover, and more mysteries to to unravel.
So to our listeners out there, I encourage you to continue this journey, delve deeper into the world of Poincaré and Betti polynomials. Explore their properties and their applications, and just see where your curiosity leads you.
Yeah, remember, mathematics, it's not just about, about finding answers. It's about asking the right questions. It's about embracing the unknown and finding joy in the pursuit of knowledge.
Thank you for joining us on this deep dive into the fascinating world of mathematics. And until next time, keep those minds curious and keep exploring. Welcome back, Deep Divers. Today we're going deep into plane curves and their connection to Poincaré polynomials. We've got a paper here called On the Addition Technique for Betti and Poincaré Polynomials of Plane Curves. And I know that sounds kind of technical, but I promise it's got some really neat math and insights. We're going to see how these polynomials reveal hidden complexity in these, seemingly simple geometric objects.
Yeah, it's fascinating how this paper connects the world of lines to the world of curves. You see, Poincaré polynomials were traditionally used for studying arrangements of lines, but this paper shows how they can also give us information about curves, especially this idea of freeness, which is basically about a curve's complexity.
Oh, so it's like using a tool from one part of math to unlock secrets in another. That's cool. But maybe we should back up for a second. We're talking about plane curves, right? Like the lines and shapes we can draw on a flat surface.
Right.
And all these curves, no matter how complex they get, they're actually described by polynomial equations, right?
Exactly. And these curves can have points of singularity.
Singularity.
Yeah, places where they might cross themselves or take a sharp turn.
Oh, okay.
These singularities are really important for understanding how complex a curve is, and that's where the Poincaré polynomial comes in. It basically captures this complexity in a nice, concise way.
So the Poincaré polynomial gives us like a numerical snapshot of a curve's singularity complexity.
Exactly. It's directly tied to something called the total Tjurina number. It's denoted as TT, and it quantifies how complex those singularities are. The Poincaré polynomial itself is defined as PCT 1 plus D1 2, where D is the degree of the curve.
The degree.
Yeah, like how many times it loops or bends.
Okay, so it's remarkable how much information a single equation can hold. But the paper also mentions something called the Betti polynomial right. How does that fit into all of this?
The Betti polynomial, denoted as BMC, gives us another way to look at it. It describes the shape and structure of the space around the curve, specifically its complement within the projective plane. So while the Poincaré polynomial focuses on the curve itself, the Betti polynomial focuses on the space around it.
So two sides of the same coin.
Exactly. And the Betti polynomial has a similar form, BMCT, 1 plus E1t plus ET2, where E represents the number of irreducible components of the curve.
Irreducible components.
Yeah, essentially how many distinct pieces make up the curve. And Thiki is the total Milnor number, which is another measure of singularity complexity.
Oh, okay. So it's fascinating how these polynomials with their variables and coefficients can tell us so much about the geometry of these curves. Now let's talk about these free curves the paper keeps mentioning. What's so special about them?
Well, free curves have a special property. Their Poincaré polynomials split into two distinct factors.
Oh, really?
Yeah, the splitting shows us a kind of simplicity in their structure. Technically speaking, a curve is free if its Jacobian ideal is saturated with respect to a specific set of variables.
So it's like the polynomial breaks apart in a specific way, and that tells us the curve is free.
Exactly. The Poincaré polynomial of a free curve looks like this. PCT, 1 plus DNT, 1 plus D2T. The D1, D2 are called the exponents of the curve. These exponents give us information about the curve's degree and its complexity.
So the exponents are like a fingerprint for free curves within their Poincaré polynomials. But is there a way to tell if a curve is free without getting into all that Jacobian ideal stuff?
There is. The paper mentions the Duplessis wall theorem. It's a test for freeness. Basically, it says that a curve is free if and only if there's a specific relationship between its degree, the number of intersections of its components, and its total Tjurina number.
No, that's handy. It's like a shortcut. Now, I'm really curious about this addition technique that the paper's all about. It sounds like we're going to be combining curves.
You got it. The addition technique is all about analyzing what happens when you combine curves. And we see how their Poincaré polynomials change. You can think of it like building with blocks. Different curves are like ingredients, and we'll see how they affect the final polynomial.
I like that analogy. So what's the main takeaway about adding curves? What does this paper tell us?
Well, the paper gives us a theorem that gives us a formula for calculating the Poincaré polynomial of a combined curve.
Okay.
So if we have two curves, C1 and C2, and they intersect at R points, and if they only have what we call quasi-homogeneous singularities, then the Poincaré polynomial of their combined curve, C1 year C2, can be calculated directly from the individual polynomials of C1 and C2.
So we can predict the complexity of the combined curve just by knowing the complexity of its parts.
Exactly. The formula is actually quite straightforward. It's PC1 Uri C2, T like PC1T plus PC2R plus C1 plus R1T2.
So we just add the individual polynomials, and then there's an extra term for the intersections. Pretty neat. But can we see an example of this in action?
Absolutely. The paper uses two curves to illustrate the addition technique. The first one, C1, is defined by the equation Q1xyz equals x plus z is xy plus x. If you could visualize it, it'd be this beautiful arrangement of lines. The second curve, C2, is defined by Q2xyz equals by2 plus y2, 2z2, which is a smooth conic section.
Okay, so one complex curve and one simpler one. How do we apply this addition technique here?
Well, first we calculate the individual Poincaré polynomials. For C1, the polynomial is PC1 t 1 plus 5t plus 6t2. For C2, it's PC2t 1 plus t plus t2. And then we see that these two curves intersect at 4 points.
So we have all the pieces. So we plug these values into the formula to find the Poincaré polynomial of the combined curve, right?
Right. When we do that, we get PC1fc2 t 1 plus 5t plus 6t2 plus 1 plus t2 plus u1 plus 3t2, which simplifies to PC1sc2 1 plus 7t plus 10t2.
Okay, so we got the polynomial. What does it tell us about the combined curve? Anything special?
Now, this is where it gets interesting. This polynomial 1 plus 7t plus 10t2 can actually be factored into 1 plus 2t, 1 plus 5t. Remember what we talked about earlier?
Wait a minute. The factored form means the combined curve is a free curve, right? Because it's Poincaré polynomial splits.
Exactly. The paper confirms this using a theorem about the freeness of specific conic-line arrangements. So by using the addition technique, they've created a new free curve by combining a known free curve with another curve.
That's really clever, like a mathematical recipe for making complex free curves from simple ingredients. But does this addition technique work for the Betti polynomial too?
Absolutely. The paper has a similar theorem for Betti polynomials. It says that BMC1 TT plus BMCT plus T1 plus R1T. It's amazing how similar it is to the formula for Poincaré polynomials.
Yeah, so just like with Poincaré polynomials, we add the individual Betti polynomials, and then there's that extra term for the intersections. Very elegant. But the paper mentions something about evaluating this Betti polynomial equation at t equals -1. What happens then?
That's a great observation. When you substitute t equals 1 into the equation, you get a relationship between the Euler numbers of the complements of the curves.
Euler numbers.
Yeah, it's a fundamental concept in topology. It basically captures the shape and structure of a space with just a single number.
Wow. So we can find a connection between the Euler numbers of the spaces around these curves just by playing around with the Betti polynomial equation. It's like solving a mathematical puzzle.
Exactly. This connection shows how powerful these mathematical tools are. They link seemingly separate concepts in these really cool and unexpected ways.
This has been a whirlwind tour. We've gone from basic definitions to complex theorems about these polynomials and this fascinating addition technique. But before we get too far ahead, I think we should take a closer look at the math behind the addition technique. The paper mentions lemma 3.1, which seems pretty important.
You're right. Lemma 3.1 is crucial. It's the foundation for the addition technique theorems. It focuses on how the total Milnor number changes when we combine curves. Remember, the Milnor number measures the complexity of a curve's singularities.
Okay, so does lemma 3.1 give us a way to calculate the Milnor number of the combined curve based on the individual curves and their intersection points?
Exactly. The proof focuses on a single intersection point between two curves, C1 and C2. Let's call it P. It says that the Milnor number of the combined curve at that point, denoted by C1, C2P, can be calculated using this formula. C1, C2P plus C1, 2P plus 2IP, C1, C2. Here, C1P and C2P are the Milnor numbers of the individual curves at that point, and IP C1, C2 is the intersection index at that point.
Okay, so we're breaking down the Milnor number of the combined curve at a specific point into these components related to the individual curves and their intersection. But what exactly is the intersection index?
The intersection index, or IP C1, C2, measures how the two curves meet at that point. It tells you how many times the curves cross or touch at that specific location. It's like a measure of how tangled they are at the intersection.
So a higher intersection index means the curves are more intertwined at that point. And that leads to a more complex singularity in the combined curve, right?
Precisely. And the formula reflects that. A higher intersection index means a bigger contribution to the Milnor number of the combined curve at that point. To get the total Milnor number of the combined curve, the proof adds up the Milnor numbers at each intersection point, accounting for both curves and their intersection indices. And then it adds the Milnor numbers of any singular points that are on the curves outside of those intersection points.
Oh, so we're carefully accounting for all the singularity complexity, both at the intersections and anywhere else along the curves. And this is what leads to the formula in Lemma 3.1.
Exactly. The formula says C1 is 2 plus 1 C2 plus 2 C1 C2, where C1 and C2 are the total Milnor numbers of the individual curves, C1 and C2 are their degrees, and R is the total number of intersection points. It's a pretty concise formula that captures a lot of complexity.
Yeah, that's impressive. But how does this lemma connect to those addition technique theorems for Poincaré and Betti polynomials? I'm starting to see how this all fits together, but I'd like to understand that link a little better.
That's a great question, and it leads perfectly into the deeper analysis in the paper. Essentially, Lemma 3.1 gives us a concrete way to see how the complexity of singularities changes when we combine curves.
Okay.
And then this understanding of Milnor numbers becomes the foundation for proving those addition technique theorems for both Poincaré and Betti polynomials. Those theorems then give us a deeper understanding of the structure, behavior, and relationships of plane curves. It all starts with this simple observation about the Milnor number at just one intersection point.
Wow, that's really remarkable. It's like we're uncovering a hidden structure within these curves, and these polynomials are the keys to unlocking that structure.
You got it. And we've only just scratched the surface of this amazing world. There's so much more to discover about these curves, their polynomials, and their connections to other parts of math.
Yeah, this is definitely a lot to take in. I'm already starting to think about curves in a whole new way. I'm definitely eager to dive deeper into the specifics of the addition technique proofs and see how these connections all play out in more detail.
I agree. Let's take a moment to process this, and then we can continue our exploration. There's so much more to discover.
Okay, I think I've had a minute to catch my breath there. We've covered a lot of ground, haven't we? From those basic definitions of plane curves and those Poincaré polynomials and Betti polynomials to that intriguing addition technique. Now, I'm really excited to dig deeper into the specifics of how those addition technique theorems are proven. Like, that's where the real magic happens, right?
Absolutely. The proofs are where we see the elegance and the power of these mathematical tools in action. So let's revisit that statement of the addition technique theorem for Poincaré polynomials. Remember, it says that if C1 and C2 are two curves with only those quasi-homogeneous singularities, and they intersect at R points, then the Poincaré polynomial of their combined curve, C1 to C2, can be calculated with that formula, PC1, C2t plus PC2t plus 2, 1 plus 4, 1, 2, 2.
Right. That formula basically tells us that we can find the Poincaré polynomial of that combined curve by just adding the polynomials of the individual curves together, and then we add that extra term to account for those intersections. But how do we actually prove that this formula always works?
Well, the proof really depends on the connection between the Poincaré polynomial and the total Tjurina number. That quantifies how complex a curve's singularities are. Remember that formula for the Poincaré polynomial, P(t) 1 plus d1t plus?
Right. The total Tjurina number C shows up in that last term of the polynomial. So to prove this addition technique theorem, we basically need to show how that total Tjurina number changes when we combine two curves.
Exactly. And that's where Lemma 3.1 comes in. It gives us that formula for calculating the total Milnor number of that combined curve, C1, C2, based on the Milnor number of those individual curves and their degrees. C1 near C2 plus sin C2 plus 2C1 C2 F4.
Okay, I see the connection now. We can use that formula from Lemma 3.1 to understand how those Milnor numbers change. But how do we get from Milnor numbers to Tjurina numbers?
Well, there's a key relationship between the two. The total Tjurina number of a curve is equal to its total Milnor number minus its degree plus the number of irreducible components. In math terms, CC, D plus E.
So we can use the formula from Lemma 3.1 to write out those total Milnor numbers of C1, C2, C1, and C2 in terms of their degrees and the number of intersection points. Then we can use that relationship between Milnor numbers and Tjurina numbers to substitute in and find an expression for C1, C2 in terms of T1 and C2.
Precisely. It's a bit of algebraic manipulation, but if you work through those substitutions carefully, you get a formula that directly connects the total Tjurina number of the combined curve to the total Tjurina numbers of those individual curves and that number of intersection points. Specifically, we find that C1a C2 plus C2 R1.
Wow, that's a really neat result. It tells us exactly how the complexity of the singularities, which is measured by that total Tjurina number, changes when we combine two curves together. Now we can use this to finally prove that addition technique theorem for Poincaré polynomials right.
Absolutely. Now that we have that expression for C1 is C2, we can plug it back into the formula for the Poincaré polynomial of the combined curve. PC1 is C2 DOET 1 plus D1 plus D2 1D plus D1 plus D2 1 D2. Remember, the degree of that combined curve is just the sum of the degrees of those individual curves. That's why we have D1 plus D2 error in that second term.
Right. And when we substitute for C1 and C2, a lot of terms should start canceling out, and we'll be left with an expression that just involve the Poincaré polynomials of the individual curves, PC1t and PC2t, and that extra term for those intersection points.
Exactly. If we do the algebra carefully, we'll find that it all simplifies down to that formula from the theorem PC1t plus PC2t plus D1 plus R1t2.
That's so cool. It all comes together so perfectly.
Yeah.
We start with this simple relationship between Milnor numbers in Lemma 3.1,
Yeah.
and then through these clever substitutions and some algebra, we end up with this elegant formula for the Poincaré polynomial of that combined curve.
It's a real testament to the power of mathematical reasoning. We've built this chain of logic starting with just a basic observation about the Milnor number at a single point, and we've arrived at this profound result about the overall complexity of those combined curves.
Okay, I'm feeling pretty good about the Poincaré polynomial theorem now. But what about that addition technique theorem for Betti polynomials? Is a proof similar?
It is. The approach is very similar. Remember that addition technique theorem for Betti polynomials states that BMC2 pli plus BMC2t plus where's R1t2? And to prove this, we again use Lemma 3.1 and that relationship between the total Milnor number, the total Tjurina number, and the Betti polynomial.
Right. The Betti polynomial formula is BMCT 1 plus D plus E1TT2. So just like with that Poincaré polynomial, we need to understand how that total Milnor number changes when we combine curves.
Exactly. And we can use that same formula from Lemma 3.1, C1 or C1 plus C2 plus 2C1 C2 plus 2C1 C2. But there's an extra little wrinkle with Betti polynomials. We also have to think about how the number of irreducible components changes when we combine those curves.
That makes sense. The Betti polynomial depends on both and E, so we need to account for both. But how do we figure out how E changes? It seems like it could get complicated if the curves intersect and break into more pieces.
You're right, it can get a bit tricky, but the paper deals with this by looking at a specific kind of intersection. It's called a transversal intersection. In a transversal intersection, those curves meet in a way that doesn't create any new irreducible components. So basically, the number of pieces stays the same.
So if we just stick to transversal intersections, then the number of irreducible components of that combined curve is just the sum of the number of irreducible components of those individual curves. EC1 plus EC2. That simplifies things a lot.
Exactly. Now, with that in mind, we can move forward with the proof, just like we did for the Poincaré polynomial. We use Lemma 3.1 to express those total Milnor numbers in terms of degrees and intersection points. Then we use that connection between Milnor and Tjurina numbers, and we remember that E doesn't change for those transversal intersections. Finally, we put all of this back into that formula for the Betti polynomial of the combined curve.
And then after some algebraic manipulation, we should get that formula from the theorem. BMC1t plus BMCT plus 1 plus 1 like 2. It's amazing how closely those proofs for Poincaré and Betti polynomials follow the same structure.
It really is. It shows the deep connections between these two polynomials and those underlying geometric ideas that govern how plane curves behave. They're not just abstract formulas, you know? They're windows into this world of intricate relationships and elegant patterns.
Well, I'm really starting to get it now. We've gone from those basic definitions of these polynomials to understanding how they capture the complexity of those curves and the spaces around them. And now we've seen how they change in such predictable ways when we combine those curves using those powerful addition technique theorems. This is all really remarkable.
I agree. It's a perfect example of how math tools can help us see those hidden structures in seemingly simple geometric objects. And the paper doesn't stop there. It also explores some of the fascinating consequences of these theorems.
Oh, yeah. I remember that bit about evaluating the Betti polynomial at T, Sangus 1, and the connection to those Euler numbers. Should we talk about that now?
Let's do it. We can explore that connection and find even more of the hidden beauty in these polynomials.
Hey, so we've really gotten into those addition technique theorems, haven't we?
Yeah.
For both Poincaré and Betti polynomials, and we saw how those proofs use Lemma 3.1 and those clever ways of working with Milnor numbers and Tjurina numbers and the structure of those curves. Now, I'm curious about that connection between the Betti polynomial and Euler numbers that you mentioned earlier. Can you remind me about that?
Of course. Remember that formula for the Betti polynomial, BMC, t plus ET2? Well, the paper points out that if we plug in t plus ET2, something really interesting happens.
Okay.
We get this. BMC lanus 1 plus D12 lands plus E, which simplifies to D12.
Okay, I see that those E terms cancel out nicely when we put in T nanus 1. But what's so special about that simplified expression, T12C? What does it have to do with Euler numbers?
This is where it gets really cool. That expression, D12C, is actually the Euler number of the complement of the curve, C, in the projective plane. So it's a single number that captures the topological structure of that space around the curve.
Hold on. Are we saying that just by plugging in T Magle's 1 into the Betti polynomial, we can get the Euler number of the complement of the curve? That's amazing.
It is. It shows this deep connection between algebraic geometry and topology. The Betti polynomial, which came from algebraic ideas, actually holds information about the shape of the space around the curve topologically.
This is pretty mind-blowing. Can you remind me what that Euler number actually tells us? I know it's a topological invariant, but the details are a little fuzzy.
Sure. The Euler number, often denoted by the Greek letter ch, is a way to describe the shape of a topological space. It doesn't matter how you bend or stretch it. You calculate it by taking the number of vertices, like corners of the space, minus the number of edges plus the number of faces. Yeah. So a simple cube has 8 vertices, 12 edges, and 6 faces. So its Euler number is 812 plus 6 equals 2. And the amazing thing is that no matter how you deform that cube, as long as you don't rip it or poke holes in it, that Euler number will always stay at 2.
I remember now. It's like a fingerprint that captures the basic structure of the shape. So we're saying that the Betti polynomial at t equals 1 gives us the Euler number of the space around the curve in that projective plane.
Exactly. It's a fascinating connection. And the paper actually takes it a step further. It uses that addition technique theorem for Betti polynomials to create a relationship between the Euler numbers of the complements of those individual curves and the Euler number of the complement of that combined curve.
Okay, this is getting pretty complex, but I'm following along. How does that relationship work?
Remember the addition technique theorem for Betti polynomials? BMC180P2 plus BMC2 plus BMC2 plus large L plus 1 T2. Well, if we plug in T in natural, I go BMC2 natural 1 plus BMC of an actual 1, and then natural linear plus CM plus R1.
Okay, I see what we're doing here. We know that BMC 9 of 1 is the Euler number of the complement of the curve C. So that equation is really a relationship between Euler numbers.
Exactly. Let's use C to represent the Euler number of the complement of C. So they can rewrite that equation like this. C1, C2 equals C1 plus C2 plus R3.
Wow. That's a pretty amazing formula. It says that the Euler number of the complement of that combined curve is just the sum of the Euler numbers, so the complements of those individual curves plus the number of intersections minus 3. It's like we found this secret accounting system for Euler numbers.
Precisely. It really shows how these abstract polynomials can reveal those deep connections between the geometry of curves and the topology of the spaces they're in.
This has been an amazing journey. We started with the basics of plane curves and those polynomials, and then we saw how those polynomials hold information about the complexity of curves and the spaces around them. We learned about that powerful addition technique, which helps us predict how these polynomials change when we combine curves. And we even found this hidden connection between Betti polynomials and Euler numbers. My understanding of all this has grown so much.
I agree. It's a great example of how mathematical thinking can help us see the beauty and elegance in the structure of things, even in those simple shapes we see all around us.
And this paper is just the start. There's so much more to explore. What else can we learn about free curves? How do these techniques work with other geometric objects? The possibilities are endless.
You said it. We've just had a glimpse into this vast world of algebraic geometry. There's so much more to discover, and who knows what amazing connections and patterns are waiting for us out there.
Well, on that note of endless possibilities and the excitement of further exploration, it's time for us to come back up from our deep dives into the world of plane curves and their fascinating polynomials.
It's been a real pleasure. pleasure exploring these mathematical depths with you.
And to all our listeners, we hope this deep dive has sparked your own curiosity about the beauty and the intricate structures that are hidden within the simple shapes around us. Until next time, keep those mathematical minds engaged and happy exploring. All right, so we're diving into this paper by Piotr Pokora. It's on Poincaré polynomials for plane curves. Looks like he's found some interesting stuff about how these polynomials change. You know, when you combine curves together. We've got the paper right here, ready to go.
Yeah, this paper, it really digs into some cool aspects of algebraic geometry. Poincaré polynomials, as you probably know, give us this way to grab information about the singularities of a curve. And Pokora's work here, it really focuses on what happens to these polynomials when we add curves together.
Okay, so I guess back to basics for a sec. What exactly is a plane curve? And why do mathematicians care so much about their Poincaré polynomials?
A plane curve is basically a set of points, and these points satisfy a polynomial equation in two variables. You can kind of think of it visually, like a curve drawn on a flat plane, right? Mathematicians love these curves because they just pop up everywhere in geometry and algebra.
And the Poincaré polynomial, it helps us understand something about the shape of the curve, or maybe like the complexity of it.
Exactly. It's like a mathematical fingerprint, kind of. The Poincaré polynomial, it encodes all this information about the singularities of the curve. Those are the places where it, crosses itself, has cusps or other sort of interesting behaviors. Really powerful tool for studying the geometry, of these curves.
Pokora is building on some previous work, I see, connecting Poincaré polynomials to hyperplane arrangements. Can you give us a little background on that?
Sure. Hyperplane arrangements are, they're basically collections of lines or planes in a higher dimensional space. They have this really rich geometric and combinatorial structure. And mathematicians figured out that you could use Poincaré polynomials to study them, to gain insights into their topology. And then later on, they extended this idea to plane curves.
So we're using tools built for higher dimensions to study these simpler curves in the plane.
Yeah, that's one way to think about it. The cool thing about math is that ideas often kind of transfer across different areas, and then that leads to these unexpected connections and insights.
Okay, so we've got our plane curves, and we've got these Poincaré polynomials. They're capturing information about their singularities. Now, Pokora is focusing on this addition technique. What does it even mean to add two curves together?
It's not addition like you normally think about it. Essentially, what you're doing is you're taking in the equations that define the two curves, and you're combining them in a specific way. And that creates this brand new curve. This new curve, it inherits characteristics from each of the original curves.
So I guess you could say merging two curves into a more complex one. Now, of course, figured out how this merging affects the Poincaré polynomial.
Right. His main result, it's theorem 3.2 in the paper. It gives us this formula that connects the Poincaré polynomial of the combined curve to the polynomials of the original curves. Plus, there are some extra terms related to how they intersect.
So if we know the Poincaré polynomials of the simpler curves,
right,
we can use this formula to predict the polynomial of the more complex one.
Exactly. It's a powerful way to understand the geometry of complex curves by, breaking them down into these simpler pieces.
Could you give us an example of how this formula works, practically?
Sure. Let's take a look at example 3.3 from the paper. Pokora considers what happens when you add a conic section, like a parabola or ellipse, to a line arrangement.
So we have one smooth curve, the conic, and then a bunch of lines all intersecting each other. What happens when we combine those?
Using his formula, Pokora can compute the Poincaré polynomial of that combined curve. And the polynomial tells us whether the combined curve has this special property called freeness.
Okay, so what does it mean for a curve to be free in this context?
It's a bit technical, but basically it means that the singularities of the curve aren't too complicated. Free curves have certain nice properties that make them easier to work with.
So by adding a simple conic to a line arrangement, we can sometimes create these special free curves.
Yeah, it is pretty neat. And this addition technique can be used to construct lots of other examples of free curves.
Okay, so we've got this powerful formula that relates the Poincaré polynomials of combined curves to the polynomials of their simpler components. What's the math behind this result?
The key is a lemma. Lemma 3.1 in the paper. It makes a connection between the Milnor numbers of the individual curves, the Milnor number of the combined curve, and the number of points where they intersect.
Hold on, Milnor numbers. What are those, and how do they relate to the Poincaré polynomial?
Good point. The Milnor number is another way to measure the complexity of a singularity. It tells us like how much the curve wraps around itself at that point.
Yeah.
And the Poincaré polynomial, it actually encodes information about the Milnor numbers of all the singularities of the curve.
So lemma 3.1 is basically saying that if we know the Milnor numbers of the original curves and how many times they intersect, we can figure out the Milnor number of the combined curve.
Exactly. And once we have the Milnor number of that combined curve, we can use other results to determine its Poincaré polynomial. That's the bridge that connects lemma 3.1 to theorem 3.2.
Okay, let's dig into this lemma 3.1 a bit more. What's the intuition behind it?
Think about it this way. When you combine two curves, you're basically merging their singularities. The lemma is telling us that the complexity of that new singularity, measured by its Milnor number, depends on two things: the complexity of the original singularities and how deeply the curves intersect.
So the more times the curves intersect at a point, the more complex the resulting singularity.
That's the idea. The lemma quantifies this relationship precisely using something called intersection multiplicity.
Intersection multiplicity, what does that measure exactly?
It tells us how tangled up two curves are at a point of intersection. If they just cross each other, the intersection multiplicity is 1. But if they're tangent to each other or have a more complex intersection, the multiplicity will be higher.
So it's like a measure of how many times the curves like kiss each other at that point.
Yeah, that's a good way to visualize it. The higher the intersection multiplicity, the more the curves are intertwined at that point.
So lemma 3.1 uses this intersection multiplicity along with the Milnor numbers of the original curves to calculate the Milnor number of the combined curve. Seems like a pretty powerful tool.
It is. And it's the cornerstone of the proofs for both theorem 3.2, which deals with the Poincaré polynomial, and theorem 3.5, which deals with something called the Betti polynomial.
Hold on. Another polynomial. We've got Poincaré polynomials and now Betti polynomials. What are those all about?
Betti polynomials are related to the topology of the space surrounding the curve. They tell us about the holes of different dimensions in that space.
So, well, the Poincaré polynomial focuses on the curve itself. The Betti polynomial looks at the space around it.
Exactly. They provide like complementary information about the curve and its embedding in the plane.
And theorem 3.5, it gives a similar addition formula for the Betti polynomial.
That's right. It tells us how the Betti polynomial of the combined curve relates to the Betti polynomials of the original curves and their intersection pattern. The proof relies heavily on lemma 3.1, which again emphasizes the crucial role of Milnor numbers and intersection multiplicity in all of this.
It's amazing how all these different concepts, Poincaré polynomials, Betti polynomials, Milnor numbers, intersection, multiplicity, they're all woven together in this elegant mathematical tapestry.
It is. It really is. That's the beauty of math. Often these seemingly disparate concepts turn out to be deeply interconnected. And Pokora's work, it just highlights these connections beautifully.
This has been fantastic so far. A great deep dive into the world of plane curves and their Poincaré polynomials. We've explored the basics of plane curves, the meaning of Poincaré polynomials, that addition technique, and the crucial role of Milnor numbers and intersection multiplicity.
Yeah, it's been great delving into these concepts with you. And really, we've just scratched the surface here.
That's right. There's so much more to uncover in Pokora's work, including his exploration of specific examples and applications of that addition technique.
Absolutely. We'll be sure to dive into those in more detail later on.
Sounds like we've got a lot more ground to cover. Stay tuned.
What's so fascinating about Pokora's work is it goes beyond just theoretical results. He actually shows us how to use these addition formulas to actually construct concrete examples of curves with specific properties.
Oh, so you mean like building new curves by combining simpler ones? Can you walk us through one of those?
Absolutely. Let's look at example 4.3 from the paper. Pokora starts with this specific type of curve called a three-cuspidal quartic. It's a curve with degree 4, and it has 3 cusps. Those are the points where the curve abruptly changes direction.
Okay, so we've got this kind of exotic curve as our starting point. What does he do with it?
He adds a line to it, specifically a line that passes through 2 of the cusps of the quartic.
So we're taking this three-cuspidal quartic, and like drawing a line right through two of its pointy bits. What happens to the Poincaré polynomial when we do that?
That's where theorem 3.2 really shines. By applying the formula, Pokora can directly compute the Poincaré polynomial of the combined curve. And what's really cool is the resulting polynomial tells us that the combined curve is also free.
So by adding a simple line to this, 3-cuspidal quartic, we create another free curve.
That's pretty cool. Does this technique always work? I mean, if we add any line to a free curve, do we always get another free curve?
Not necessarily. It depends on how the line intersects the original curve. The choice of line in Pokora's example, it's very specific. It has to pass through two of the cusps to make sure the combined curve stays free.
I see. So there's like an art to this addition technique. You need to choose your curves and your intersection points carefully to get the result you want. Exactly. And Pokora's paper, it gives us the tools to make those choices strategically. He goes through various examples showing different ways to combine curves and the properties that come out of that.
Okay, so we've seen how this addition technique can be used to construct new free curves. What other applications does it have?
Well, remember we were talking about Betti polynomials?
Yeah.
They tell us about the topology of the space that surrounds the curve.
Right, the holes in the space around the curve.
Exactly. Pokora also uses this addition technique to study those Betti polynomials. For example, he shows how to use addition to compute the Betti polynomials of complements of certain arrangements of lines.
Complements. Can you remind us what those are again?
Sure. The complement of a curve. It's basically everything in the plane except the curve itself. It's like the negative space around the curve.
So we're looking at the holes in the space outside the curve, not inside it.
Precisely. And it turns out that the Betti polynomial of the complement can tell us a lot about the geometry of the curve itself. Pokora's work gives us tools to analyze these complements using the addition technique.
It seems like this addition technique is a pretty versatile tool. We've seen how to use it to construct new free curves, study Betti polynomials, and gain insights into the topology of complements. Any other surprises Pokora has for us?
One really interesting aspect of his work is the connection he makes between the addition formula for Betti polynomials and something called the Euler characteristic.
Euler characteristic. That rings a bell. Isn't that a topological invariant?
You got it. The Euler characteristic, it's a number that captures some fundamental information about the shape of a topological space. It's invariant, meaning it doesn't change, even if you like bend or stretch the space.
Okay, so how does this Euler characteristic fit in to the story of Poincaré polynomials and addition?
Pokora shows that. When you substitute a specific value into the addition formula for the Betti polynomial, you get a relationship between the Euler characteristics of the complements, the original curves, and the Euler characteristic of the complement, of the combined curve.
Hold on. So by plugging a number into this polynomial formula, we get information about the Euler characteristic, which is a totally different topological concept. That's a neat trick.
It is. And this connection, it really highlights the deep interplay between algebra and topology that you see throughout Pokora's work. He's constantly bridging these two areas, revealing all these surprising links between concepts that seem totally different at first glance.
It's like he's weaving this rich tapestry of mathematical ideas with threads connecting geometry, algebra, topology.
That's a great analogy. And the beauty is that tapestry is still being woven. Pokora's work opens up all these paths for more research and exploration.
Okay, before we get to, lost in the grand scheme of things, I want to circle back to lemma 3.1. It seems like this lemma is the real workhorse in Pokora's paper. It underpins both the addition formula for Poincaré polynomials and the addition formula for Betti polynomials. Yeah. Can we dive into the proof of this lemma and see how it all works?
Absolutely. It's definitely worth taking the time to understand the inner workings of this really crucial result.
So lemma 3.1 relates the Milnor number of the combined curve to the Milnor numbers of the original curves and how they intersect. How does the proof go about establishing that connection?
The key ingredient in the proof is this formula from singularity theory. This formula connects the Milnor number of a singularity to something called the intersection multiplicity of the curves at that point.
Right. We talked about intersection multiplicity before. It measures how tangled the curves are at that intersection point.
Exactly. And this singularity theory formula tells us that the Milnor number of a singularity at a point is related to the sum of the Milnor numbers of the individual curves at that point, plus twice the intersection multiplicity minus 1.
Okay, so that formula
Yeah.
gives us a way to calculate the Milnor number of a singularity from the Milnor numbers of the original curves and their intersection multiplicity. How do we use that to prove lemma 3.1?
The idea is to apply this formula to each intersection point of the two curves and then add up all the results. The sum of the Milnor numbers of the combined curve at all the intersection points will give us the total Milnor number of the combined curve.
So we're basically adding up the complexities of all the new singularities, taking into account the complexities of the original singularities and how the curves intersect.
Precisely. And when you do the math, making sure you account for all the terms, you get the formula stated in lemma 3.1.
Can you walk us through a specific example? See how that works in practice.
Sure. Let's say we have two curves, C1 and C2, and they intersect at a single point P. Let's say the Milnor number of C1 at P is 2 and the Milnor number of C2 at P is 3. And let's say the intersection multiplicity of the two curves at P is 4.
So we've got two curves with, some moderate complexity at their intersection point, and they're pretty tangled up there.
Right. Now, to find the Milnor number of the combined curve at P, we can use that singularity theory formula.
It tells us
that the Milnor number of the combined curve at P is 2 plus 3 plus 2 times 4 minus 1, which equals 12.
So the complexity of the new singularity at P is 12, which is significantly higher than the complexities of the original singularities. Makes sense? Because the curves intersect with high multiplicity, making the combined singularity more intricate.
Exactly. And we can repeat this process for every intersection point of the two curves. Summing up the Milnor numbers of the combined curve at all those intersection points gives us the total Milnor number of the combined curve, which is what lemma 3.1 gives us.
This walkthrough of the proof has been really helpful. It's amazing to see how this seemingly simple lemma relating Milnor numbers and intersection multiplicities forms the foundation for these really powerful addition formulas for Poincaré and Betti polynomials.
Yeah, I agree. It's a real testament to how interconnected mathematical concepts are and the beauty of, elegant proofs.
It feels like we've covered so much in this deep dive. We've explored constructing new curves using addition, the connection between Betti polynomials and Euler characteristics, and the intricate details of the proof of lemma 3.1.
It's been great navigating this mathematical landscape with you.
Before we wrap up, I'm curious about one more thing. Pokora's paper focuses on plane curves, which are, relatively simple geometric objects. Do these ideas extend to more complex objects in higher dimensions?
That's a fantastic question, and it's actually an active area of research in algebraic geometry. Mathematicians are working on ways to generalize concepts like Poincaré polynomials, Milnor numbers, and intersection multiplicities to higher dimensional space.
So the ideas we've been discussing today could potentially be applied to study surfaces, solids, and even more exotic objects in higher dimensions.
Exactly. There's a whole world of mathematical possibilities waiting to be explored. And Pokora's work provides a really solid foundation for those future investigations.
This has been a really stimulating deep dive. We've uncovered a ton of mathematical gems hidden within Pokora's paper.
I agree. It reminds us that even these seemingly abstract math concepts can have really far-reaching implications and connections to other areas of math and beyond.
Well said. I'm excited to see where these ideas lead us next. Stay tuned for more deep dives into the fascinating world of mathematics. I'm really struck by just how elegant Pokora's results are. It's amazing how he's connected all these seemingly disparate concepts like Poincaré polynomials, Betti numbers, Milnor numbers, even intersection multiplicities, all into this coherent framework.
I agree. It really speaks to the power of abstract mathematical thinking. By developing these sophisticated tools, we can, uncover these deep connections between different areas of math and get a deeper understanding of the geometric and topological structures that underlie our world.
Speaking of uncovering connections, I want to dig a little deeper into that relationship between the addition formula for Betti polynomials and the Euler characteristic. Can you remind us again how that connection works?
Of course. So remember theorem 3.5? It gives us a formula that relates the Betti polynomial of the complement of the combined curve to the Betti polynomials of the complements of the individual curves, along with some terms that depend on their intersection pattern.
Right. That formula with all the sums and products of polynomials.
Exactly. Now, here's the cool part. If you substitute t equals -1 into this formula, something really magical happens.
Magical. I love when math gets magical. What happens?
Well, when you make that substitution, the formula simplifies, like dramatically. And the terms that are left have a very specific interpretation. They actually give you the Euler characteristics of the complements of the curves.
So by plugging in a specific value for t, we go from this, like complicated polynomial formula, to something that tells us about the Euler characteristic.
Yeah.
Which is a totally different topological concept.
That's right. And this connection, it's not just a coincidence. It shows us there's a deep relationship between the algebraic structure of Betti polynomials and the topological invariant of the Euler characteristic.
Can you give us a more concrete sense of how that works? Maybe with a specific example.
Sure. Let's say we have two curves, C1 and C2, and we want to calculate the Euler characteristic of the complement of their union, C1 union C2. Let's use the Greek letter chi to denote the Euler characteristic of a space X. So we write it as chi of X.
Okay, so we want to find chi of the complement of C1 union C2.
Exactly. Now, if we use theorem 3.5 and substitute t equals -1, we get this relationship. Chi of the complement of C1 union C2 equals chi of the complement of C1 plus chi of the complement of C2 plus I minus 3, where I is the number of intersection points of C1 and C2.
So the Euler characteristic of the complement of the combined curve equals the sum of the Euler characteristics of the complements of the individual curves plus the number of intersection points, minus 3. That's a surprisingly simple formula.
It is, and it lets us calculate the Euler characteristic of the complement of a complex curve by, breaking it down into those simpler pieces.
This connection between the addition formula for Betti polynomials and the Euler characteristic. It's truly fascinating. It shows how these different math concepts can be like intertwined in these unexpected ways.
I couldn't agree more. It's a real testament to the beauty and depth of mathematics. A lot of times, the most profound insights come from exploring those connections between areas that seem totally unrelated.
Looks like we've reached the end of our deep dive into Pokora's paper. We've explored his main results, gone through the proofs, and even found some surprising connections to other mathematical concepts.
It's been a great journey, filled with intriguing insights and mathematical elegance.
I'm really looking forward to our next deep dive.
Until then,
keep exploring, keep questioning, and keep diving deep in the boundless world of knowledge.